Machines are specialists, whereas we tend to think of humans as generalists. And we see machine learning models with about 100 billion parameters, whereas humans have around 100 trillion connections in their brain. So this is a factor of 1,000, and this gap is closing fast. And we can broadly say that machines have superhuman performance on many specific tasks, so long as those specific tasks are well-defined and formulated. Well, let's start from some broader neuroscience motivation. The human brain connectome contains 100 billion neurons. The cat brain contains roughly 1 billion neurons. And our brain contains roughly 100 trillion connections, where each of our neurons connects to 5K to 200K of 10K different types of neurons. The recent GPT-3 transformer model used in NLP and natural language processing was trained by essentially omitting words and predicting them and knowing the relationship between two consecutive sentences or paragraphs, whether they follow each other or not. And these models usually are built on encoder-decoder architectures with attention, and the latest one has 175 billion parameters. Right? If we go back 2 years ago, we had a few hundred million with BERT, and now we're on 175 billion. So this is still 3 orders of magnitude less parameters than the number of connections in our human brain. I'm not implying that there is any comparison here in the functionality or what this can do. I'm just counting the number of connections. So here's the human brain number of connections on the right, 100 trillion. And here are all these models zoomed in just for scale and the number of parameters they have. So this is just giving us a sense of scale where we are in the larger scheme of things for general motivation. Another motivation comes from machine learning systems. Quite a lot of work has been done on what I like to term Alpha X. So this is AlphaZero and AlphaGo in board games, chess, shogi, Go, AlphaStar in multiplayer online games, AlphaFold protein structure predictions. These are all works from DeepMind. AlphaD3M on automated machine learning. This is some of our work. AlphaStock on stock trading, and some other recent work, Alpha Dogfight. It's actually a fighter pilot AI, which is superhuman. And the list goes on. There are several dozens if you look at the projects and literature. And so each one, you can consider each one of these as a very narrow domain. And it's very different than the human brain, right? It's a very narrow domain, but they are on a league of their own, where it will be very difficult or impossible to compete in these domains right now, in each of these domains and many others, with these algorithms. Essentially, if you look at chess, it's completely, ELO ratings are in a league of their own. And the last one in fighter pilots, again, the humans don't stand a chance in this case. So there is a gap here between the superhuman performance in specific tasks and the general intelligence that we have. The work today on self-driving that's commercial in various companies stemmed from 2 decades ago. The challenge was a grand challenge for self-driving in the desert from DARPA, and it was a competitive effort. Today, in the past 4 years, various challenges from DARPA were collaborative. One of them is data-driven discovery of models, which is AutoML, which pioneered AutoML 4 years ago. It's a collaborative effort between 250 researchers from top universities across the US. Learning with less labels, it's few-shot learning, lifelong learning, which is online learning, and machine common sense. So we'll talk about definitions of things you know, supervised learning, and then move to transfer learning, meta learning, and AutoML. And after that, I'll explain a few variations called adaptation, also called semi-supervised or unsupervised transfer learning, multitask learning, few-shot learning, and online learning. Okay, so let's begin. It's some math and definitions. First thing is that we have an observation in the world. So we have some input X. It could be a d-dimensional vector. And we have a function mapping that x into an output scalar y. Okay. And here's, not in words, but in notation, f maps x to y. And today we'll take this view, but we will look at by the end of the lecture, we'll start looking at a Bayesian perspective and talk about inference in the real world. We have probabilities over x and over y conditioned upon x. And if we have multiple observations, then instead of just a column x, we have a matrix, an input matrix x, d times n, where m is the number of examples, and a function, an output, which is a label for each of these vectors. So you just take, instead of one example, we're taking m examples, putting them as columns, passing them through f, and getting a label for each one of them. Okay, this is a supervised learning setting, right? You have a task, you have a learning algorithm, and that learning algorithm outputs a predictor. So formally, we have data. That data contains x's and y's. X is our matrix of examples, and y are our labels. And we have a learning algorithm denoted here by G, and it outputs a predictor. Ftag is an estimator of f. F is something we don't know, and we want to estimate it. And so ftag is G of D. And now in supervised learning, we have our data, we have a learning algorithm. We estimate a predictor ftag, and we take test data xtag to make predictions ytag. Okay? So mathematically, we have ftag equals G of D, and ytag equals ftag of xtag. Okay, this is supervised learning. So what is transfer learning? So let's just start with a simple story. I started teaching at Columbia University 3 years ago, in 2017. My daughter at the time was 10 months old. Today she's 4. She goes to Harvard's preschool here. And when she was 10 months old, we had a picture at home of a horse by a painting called Gutmann. And I knew she recognized the picture, because whenever she recognized the picture and we sang a song related to horses, she would laugh and respond. But I was quite confident that except for maybe a few horses in Central Park, she didn't see a lot of horses. So I'm pretty sure she didn't see 50,000 horses at 10 months, and maybe just 100. But yet she could still recognize that and recognize the class. So the question is, what was she doing, or can we emulate this process? Well, if we look at transfer learning, or learning from a small data, then the idea is that we take a large corpus of data, have a learning algorithm produce a base predictor, and then those are all the images that she saw until she was 10 months, whether there were horses or not, everything, or not horses. And then take a transfer learning algorithm and that base predictor with the new data, just the images of horses, and create a predictor for horses. The new data here is very small, and the data on the left is very large. Now, formally, the data on the left is D, X and Y. G is our learning algorithm that creates our base predictor ftag from the large data. And gtag is our, so G is our learning algorithm, and gtag is our transfer learning algorithm, which takes the small data set of horses, dtag, and creates this f hat for classifying horses. And then there are variations on this. What is adaptation? Well, sometimes that is referred to unsupervised transfer learning. So if you remember the mathematical formulation for transfer learning here, instead of given new data, dtag, we're given just xtag. Okay, it's unlabeled. Like an example of adaptation, I surfed, snowboard, and skateboard, but probably doing these activities helps, and you might be able to learn how to do one of these activities and adapt from ocean to snow to concrete. but also in images if you recognize these images. In the narrow sense, and I'll start with the narrow sense of definition of meta-learning. In meta-learning, we have a task which is simply data splits and priors. So we have data, each task data pairs here are just a set of data with a small set of data with, say, training and test. Okay? So you take your images and you can split them into many groups of data training and data test. And then you have a meta-learning algorithm whose output is a learning algorithm. And when we're given a new task and data, that learning algorithm that we created outputs a predictor. Formally, here's the math. We have sets of data sets, D1, D2, till Dn, denote them by S. We have a meta-learning algorithm denoted here by H, and the meta-learning algorithm outputs, let's call it GTOG here, which then operates on DTOG to generate F hat. So this is the picture. We have many data sets, a meta-learning algorithm. It outputs a learning algorithm, which then gets another data set, which outputs a predictor, which is then given test data and results in predictions. Okay? And here are all three equations at a high level. Again, we haven't discussed the probabilistic setting, but at a high level, the narrow definition of meta-learning can be seen here. GTOG is H of S, F hat is GTOG of DTOG, and Y hat is F hat of X hat. And I've omitted all the parameters here just for the sake of simplicity, and we'll see all the parameters, theta, phi, etc. We're learning to learn a learning algorithm. Whereas in machine learning, you had a learning algorithm. Here we're learning that learning algorithm, and we're talking about the meta-learners. Okay, now this is a narrow view. Why did I say, why is this a narrow view? Well, it's a narrow view because machine learning systems contain much more than just an estimator or a predictor. And a predictor is usually part of a larger machine learning system or data science pipeline or system. And usually a machine learning system is built from some primitives, machine learning primitives, and you can think about machine learning primitives such as all the functions in scikit-learn, including pre-processing, post-processing, feature extraction, feature selection, and estimation. You can think about machine learning primitives as all the libraries you've seen in machine learning, whether it's deep learning or others, TensorFlow, PyTorch, others, etc. And you can think of machine learning primitives as algorithms, as machine learning algorithms, like PCA, SVM, neural network, etc. So an example of a machine learning pipeline would be some pre-processing, feature extraction, prediction, and post-processing. And here is an example. So the three tenets of machine learning are the data, the task, and the solution. In meta-learning, we're looking not only at the data, we're looking at metadata about the data. We're looking not only about the task, but metadata about the task. And not only the solution, but also metadata about the solution. And the solution, which has metadata about the solution, can be represented, for example, as a pipeline that takes in data, performs pre-processing, feature extraction, feature selection, estimation, and post-processing. So why is this a broader view? Well, now in automated machine learning, we have an AutoML algorithm that generates a learning algorithm. But the difference between AutoML, one of the differences between AutoML and meta-learning is that in AutoML, the input is not just the data set into buckets of training, test, training, test, training, test. It's, say, 1,000 data sets for classification, task 1, 1,000 data sets for regression, class 2, 1,000 data sets for graph matching, etc. And you can have hundreds of tasks. And by tasks, I mean binary classification, multi-class classification, regression, etc. A task isn't defined by the narrow definition of splits of data to train and test. And then the new data for a task, say given classification problem, is handled by a learning algorithm that the AutoML algorithm generates. So the AutoML algorithm learns to generate a learning algorithm, and then that learning algorithm handles a data set that it has never seen before, creating a machine learning system that then takes in the test data and does prediction. We can think about a learning algorithm that generates an output of a machine learning pipeline. So the learning to learn paradigm, if in machine learning we learned parameters of a model of M, where M was a classifier or a machine learning pipeline, or a machine learning algorithm, or a reinforcement learning method for that matter, in learning to learn, we learn M and the parameters at the very basic level. But as you can see here, automated machine learning extends far beyond a narrow definition. In multitask learning, we are given multiple tasks, and we have a multitask learning algorithm that outputs multiple predictors. So you want to learn these tasks simultaneously. In zero-shot learning, we have a zero-shot learning algorithm that takes in these tasks and outputs a predictor. And that predictor can work on a new metadata of a data set. And that's very useful if we have an example that we don't have labels for. In online learning, which is probably some of the things that humans do online, sequential, etc. So when we learn courses, we learn prerequisites, we learn the elementary school courses, and we built on these courses to learn new things. We have a data and task that we learned, and then an online learning algorithm that comes up with a predictor. And then more data come in, and we again devise an online learning algorithm and a predictor, and et cetera, et cetera. And this continues on and on. Okay, so you can think of various tasks that in humans, it's crawling, walking, running, riding a bike, etc. You don't learn the last thing without everything beforehand. So it's not learning from scratch, it's learning online, sequential, or lifelong learning. We had a task, and we used optimization to learn that task. And using neural networks, these were relatively easy tasks. The other perspective is that we could have a learning algorithm that instead of solving a task by optimization, think of it in the reverse direction, the learning algorithm is the one that is proposing the new task. So flip the arrow. Take an algorithm that decides what's the next task rather than solving it. And then you can solve it. But first, let's flip these arrows. So here we have the meta-learning paradigm with tasks and a meta-learning algorithm, and we're solving this by optimization. Well, another food for thought is let's flip the arrows. Let's have a learning algorithm whose goal is to produce the tasks rather than just focus on the data flow from task to learner. Let's focus on learner to task as well, because learning new tasks and doing new tasks is what children and humans do all the time. Like, we're really good at solving and optimizing for specific tasks. So in multitask learning, we see the tasks on the left and a multitask learning algorithm where the arrows are from task to the multitask learning algorithm. And again, this is solved by optimization. Let's flip the arrows and look at the reverse direction of generating these tasks. Well, generating these tasks, a special case of that is selecting the tasks. So before we look at just generating new tasks, which seem difficult, let's look at the way we can simply decide a curriculum of which tasks or samples to train on first, and do that from easy to hard. So essentially start by training on the easy examples and then train on the harder examples, whether it's supervised learning, semi-supervised learning, self-supervised learning, or reinforcement learning. When we learn to read, if someone gives us the full text of the book in first grade, we probably won't learn anything. We need to learn gradually. One simple example is appending a loss on top of any existing loss. So you take your standard training neural network, you append a super loss, and that super loss downweights the contributions of the hard samples, namely those that have a large error. Other approaches that generate tasks, not just the narrow approach that we just relatively narrow, it is wide, but curriculum learning is to look at the problems not as an optimization problem, but from a game theoretical standpoint. And now we can look at the entire mechanism of n players and the pairwise interactions between each two players, and look at the entire system and maximize the function G over the utility functions of all the n players. Okay, so these are approaches that essentially move us towards generating new tasks rather than just optimizing existing ones. Self-supervised learning, important to see that state-of-the-art methods don't even need negative examples. So in this case, the network takes an image, takes two augmentations of the image. The top network and the bottom are the same. The top network is passed to a predictor, and the label in the predictor, rather than it being the rotation transformation on the original image, the latent itself, is the label. Now, where does that label come from? Just from the copy of the old weights of the network on another augmented view, and those are the latents from the same network with other augmentations. So essentially, this is bootstrapping, and this is a general purpose self-supervised learning architecture that works really well and is now state-of-the-art over contrastive methods. And we will start with a motivational example, moving from learning multiple games, such as Atari games, to learning entire fields, such as courses. Then we will discuss motivating examples of multitask learning, such as self-driving cars, edge devices, cross-lingual translation, and NLP, and other applications. We will formulate multitask learning mathematically and see various solutions with various MTL architectures, hard sharing, soft sharing, and hybrid sharing. Then we will formulate the sharing as a multi-objective optimization problem and see a solution coming from the optimization community, and then look at the broad problem as a combinatorial optimization problem and a solution to an NP-hard problem, and finally discuss a few applications. Let's start by just a bit of motivation and some progress in the field in motivation. You're probably familiar with DQN that came out in 2015, which was a deep reinforcement learning algorithm that played 57 different Atari games, right? Different games here back from the 80s or 90s. And when it came out in 2015, it played some of them at superhuman level, above human level. You can see here the line, and quite many games below human level. But that was in 2015. And what quickly happened within the next 3 years is that researchers in the machine learning community worked on the harder problems, the sparse exploration problems where you had sparse rewards, etc. And within 3 years, the problem that was random in 2015 became at the level of the top problem that was in 2015, today at superhuman. So today the machine plays all of these games indefinitely, okay? And that happened in 3 years, and then, you know, there is a single agent that plays in 2020 all of these games at superhuman level. So not, and this is an example, if you will, for a multitask agent that's playing 57 games all at superhuman level. In our learning to learn paradigm, right? And you can see the various topics: college-level mathematics, physics, chemistry, computer science, electrical engineering, and machine learning is also there. And on the right, you can actually see the performance of few-shot learning of GPT-3, though this is just between 0 and 5-shot learning. So this is not 50-shot learning. This is just 5-shot learning on all these topics. What is striking here is that, US foreign policy, GPT-3 does 70%, or marketing, 65%, 66%, but the hardest ones that are slightly above random are chemistry and physics, okay? And so what will happen here, this is my prediction, but my prediction is that since this benchmark now, GPT-3, without any modifications, just few-shot learning, just 0 to 5-shot learning is performing this, and the needle is already moving if you do more than 5-shot learning, that the machine learning community will now work on university-level chemistry, physics, math. Machine learning does it slightly better, until these are at the top in a similar fashion that those 57 games that DQN came out in 2015, eventually were all superhuman. That learning to learn courses instead of learning games, what we did focus on learning games. Now, part of the machine learning community will focus on learning entire topics, entire fields. And this is quite a leap in terms of goal. People will be satisfied once the last topic is solved, which will probably leave self-conscious and other things for humans. The machine still is not aware that it is solving questions in these topics. It just solves those. But that's another topic, okay? And so that was just a motivating example, and the pace at which progress is being made, I think it's really exciting. Let's go back to the actual formulations and the math and formulate the multitask learning problem. We have tasks and data, and multiple of those, and we have a multitask learning algorithm whose goal is to create predictors, one for each task. So you have n tasks, and you have data for these tasks, and the output is n predictors for these tasks. And there's a multitask learning algorithm that creates these predictors. Here is an example of the tasks that the Tesla Autopilot self-driving performs, and these includes detecting cars, pedestrians, signs, lights, curbs, lanes, crosswalks, etc. You can see those tasks being performed on the bottom, and you realize right away that there are many, many tasks performed here. Okay? And these tasks might also have subtasks, but this is in an order of 50 to 100 tasks. If a task is detect cars or detect pedestrian, and then there are different types of signs and lights and etc. And you can think about localities and other intricacies here. So this is a multitask learning problem. We want to know how to solve this, and just looking at this, we need to figure out a way how to go about this, solving all these tasks. Here's another example, edge devices. So you have a mobile phone or a black box, and you have an image, and you'd like to perform multiple tasks such as normal estimation, depth estimation, or segmentation on this image, right? Maybe this is something that you'd like to perform on your mobile device in real time, and you'd like your camera to process the image, get the depth, the normal, the segmentation, the image, and other properties. You'd like that to be really fast, both for training and inference, and you like high performance, like very good prediction accuracy. And you want this to be on your mobile device, so it needs to be compact in the sense that a few hundred gigabytes is compact and not 175 billion parameters, right? So this is a very important application. We're all using mobile phones. So let's talk about solutions, or what are the problems here? Well, let's look at the architectures that we can naively suggest. One naive approach would be an all-in-one network. So one network to rule them all, a network that does all the tasks, right? That's one approach. Another approach, which is completely 180 from this one, is a separate network for each task. So you'd have an individual network for every task, right? And there are hybrid approaches in between, right? And the way we described it earlier, we described it as if there was a separate network for each task, but essentially that network can be on a shared backbone. Okay, so even though the graphical formulation was as if there were a predictor for each task, you can see that it might be useful to have a neural network that learns multiple tasks at once, I guess. It might not be feasible to have 100 neural networks in your car and train each one individually for every task, right? And the same for your edge device. So this turns out to be a combinatorial optimization problem, matching tasks to networks and which networks perform or on which tasks. So a network can perform multiple tasks, and so one network can work on multiple tasks, and there is a relationship here. And if you look at this, this is an NP-hard problem, matching between the set of tasks and the set of networks. Okay, so now we reach a few questions that are just a few things that we'd like to think about before we come up with solutions or present the solutions in the field. The first is, how do tasks influence each other? Does a task help another task? Is there negative transfer? For example, if you compute the normal map or the depth map, these tasks are probably related and may help each other. But maybe there are other tasks that actually have negative transfer effects, that if you optimize for one task, you ruin another if they share the network. The second question that you might be wondering is, how do you even share the weights between the different tasks if you have networks that solve multiple tasks and share weights? It would be interesting to know how the network size or capacity influences multitask learning, and how the dataset size and the distribution of the number of samples per task influences. Maybe we have a scenario where we have the same number of samples for each task, but maybe the distribution is skewed. Maybe we have a lot of samples for many tasks, but just a few for a few tasks, we have just a few samples. Okay, and this also relates to whether, these questions relate to whether the tasks are similar or not. Are they heterogeneous or they're similar? I mean, learning to answer questions in biology or math or chemistry or foreign policy, these seem very different when we look at these questions and these tasks, right? Okay, so let's start by heterogeneous tasks. Well, by heterogeneous, meaning not the same, we can talk about difference in importance of the task, the difficulty, the different number of samples, the noise level, etc. So, right, the world is heterogeneous, the tasks are also. And so let's start by a definition. Here is an example of a shared backbone for multiple tasks with multiple heads for each task. So we have an input X, example X, and a set of tasks 1 through T. And the output of task T is YT. Could be, is there a car in the image? Is there a pedestrian in the image? Is there a stoplight? Is there a stop sign? Is there another sign, etc.? And each of these would be an output. And you have a certain number of data points, and the data would maybe sampled IID. So the data would have the image xi for I equals 1 to n for n images. And for each image, you'd have a label at the end for each task. So for each task, you'd have a label. So this is not a softmax. These do not sum to 1. It's not probabilities over all the classes, etc. because it could be something like 0 or 1 or a one-hot vector denoting whether this class is present or not, and that doesn't sum to 1. Okay, so a data point here is both an input example X and the set of output tasks for that sample I, Y1 through YT, for all the tasks 1 to T. Okay, and so we might have an architecture like this with a shared backbone network, and those are shared weights, theta of S, and task-specific layers, theta 1, theta 2, until theta T, 1 for each task. And more formally, we can call the shared backbone network F, with shared backbone parameters theta of S. These are denoted here in gray. So these circles in gray denote the network, the shared backbone network F. This part of the network has parameters theta S. And each task has a task-specific decoder network that's denoted by GT for T equals 1, 2, 3, or task A, B, C, with task-specific parameters theta T, theta 1, theta 2, etc. And then that means that we can define a task-specific loss, LT, of theta, given theta S and theta T, which is just the average over the total of the sum of the losses, in this case, over all the samples, the average over all the samples I, of the loss of T. We might put some alpha T here to weight the losses, GT of F of X, theta S, theta T, and YT, which is the ground truth. Okay. Now notice what we did here. L of theta is just a linear combination of the losses, the individual losses of the tasks. When we're looking at minimizing theta, that includes both the parameters that are shared and the parameters that are specific for each task, and we define a total multitask loss function here, what are the advantages and disadvantages of these formulations? Okay, so take a look at this expression. You have T tasks, or tasks small t going from 1 to capital T. Alpha T is just a coefficient that can be a scalar for each task summing to 1. So sum of alpha T, T equals 1 to T, sum to 1. And you do a linear combination of the losses. What are the advantages of this approach? What can be disadvantages? Well, the advantage is that this is simple. We simply sum losses and optimize for this. It's a simple objective, but there are many disadvantages. How do we select the weights? How do we define the loss? So do we develop loss weighing strategies? How do we define individual losses? The performance eventually will be dependent on these weights of each individual losses. And I'm sure you've all seen a paper or research or a problem where you optimize more than one objective, and you did that by simply summing them up. And in style transfer, we saw that. There was a content loss and a style loss, and there was this alpha parameter and 1 minus alpha, and we summed the style loss with some value and the content loss. Well, it turns out that this formulation only handles a convex part of a Pareto front. We would need to change this formulation of our total multitask loss. Instead of total, and this can also be called linear scalarization. It's very common because it's very simple. It's the go-to strategy when you have multiple objectives. But we will see that in operations research and information engineering, there is a different formulation called multiple objective optimization. And we will replace this. But this coarse approximation in computer science, computer vision, people usually use this. In the operation research community and optimization community and economics community, people look at Pareto fronts, they look at multiple objective optimization we will discuss today. So let's not take this combination of losses as a given, and let's say, well, this has an advantages, but also many disadvantages. Not only that do we need to find the weights, we might need to define the loss functions, but also it doesn't handle the entire space. Okay, it's a linear combination of losses. So there is a justification for doing this, and one example may be, for example, we have one solution theta that may be better for task T1, whereas another solution theta tag may be better for task T2. So if we have these two solutions, theta and theta tag, the loss of T1, which is dependent upon the shared parameters theta s and the task-specific parameters theta T1, may be less than the loss for T1 given theta tag, whereas the loss for T2 given theta may be greater than the loss for T2 given theta tag for tasks T1 and T2. Solutions may not be comparable because there are multiple tasks, and you can think of these tasks as multiple axes, and you can have a solution that's better for task 1 parameters and another solution that's better for task 2. Okay, if you just take the total loss to be the sum. Okay, so we need to rethink this objective. This is the first setting, and it's called hard sharing because you have a shared backbone network, and you share the weights in early layers, and then you split into backbone and task-specific layers. So when you look at this architecture, and this is just one network to rule them all with a shared backbone and task-specific layers, what are the advantages and disadvantages that you can see just by looking at this architecture? A question that we see here right away is, where do we split? What's shared and what's not shared, right? So that's another question. But advantages can be efficient runtime. Disadvantages can be oversharing. And like you have overfitting here, you might have oversharing and negative transfer between different tasks. Negative transfer is when you have two tasks that when you train them and optimize for one task, it actually ruins the weights and the performance of another task. When you're trying, these are like conflicting objectives. Okay, but we'll formalize that mathematically. Another alternative, which is the other extreme, is individual network for each task. And here we see an individual network, so the input is passed through the network in red and the network in green, the network in blue, and these are individual networks, and there's no sharing of weights, it's decoupled. What are the advantages and disadvantages of an individual network for each task? So there's no negative transfer between tasks. The disadvantage is that this might be inefficient in runtime. It would not scale well with the number of tasks. If you have hundreds or thousands of tasks and you need to build these networks for each task, it would not scale. So, but this gives us a thought. If we could look at each of these networks, the red one, the green one, and the blue one as a node, as a network, and each of the tasks as a node, maybe we can match tasks to networks and have more than one network solve a task and see which networks we need, which networks we don't, and make some hybrid approach. And so individual networks tend to perform well, but they have all these disadvantages. But if we do have the compute resources and the data, and we can have them perform well, though they are not sharing things between different tasks, and that's a waste. So what is negative transfer as promised? Well, why does training individual networks often work better than a shared network? Well, the relationships between the tasks determine if shared architecture works well or not. And negative transfer results from one task that may dominate the training. Tasks may be learned at different rates. You might learn one task quickly and the other task takes more time. And if you're sharing an architecture, then you're performing the same algorithmic steps for learning, and you're not adapting. And the gradients may conflict. If you think about the loss landscape of these multiple tasks, right, as we define this. And so you can, all these are defined as negative transfer. Okay. What is good about having a model trained on multiple tasks at once? Well, if you do have such a network, it will be more robust to adversarial attacks on individual tasks. So let's look at solutions and start from architectures, and then we'll go through the math. So we'll start from showing a few architectures, then we'll do multi-objective optimization, and finally combinatorial optimization. So the architectures are hard parameter sharing, soft parameter sharing, some ad hoc sharing, and learning this sharing. These are the hybrid approaches. So you have hard, you have independent, or another division would be independent, one network, and some hybrid. But this is also a categorization. So hard parameter sharing, we've seen, we share information in some early layers, we split the network when we define loss functions. There's hard sharing backbone and task-specific layers. We saw that already. Now let's change our objective. Let's look at optimizing a collection of possibly conflicting objectives. So if we define the shared parameters theta s and the task-specific parameters theta 1 through theta t, we can minimize theta s, theta 1 to theta t, such that we minimize the loss for the first task and the loss for the second task and the loss for the tth task, and minimize this point under find theta s, theta 1 to theta t that minimize this multi-objective. So this is multi-objective optimization, and we'll reach that later, but this is under the regime that we're doing some parameter sharing with a backbone. So if we have a backbone that we're sharing, then we can either learn that or use multi-objective optimization and handle that rigorously. Specifically, if the tasks are 1 to t, and we can consider optimization, so instead of theta, I'm moving to x, so I just change notation. X is simply the neural network parameters, and it includes theta s and theta 1 and theta 2 and theta t. So we can think of this as a multi-objective function, f of x, from Rn to Rt. F of x is just f1 of x to ft of x. And the objective function of task t is it has a task-specific loss, f of t. And so f of t of x is just the loss from Rn to R. And we'll see a formulation for that. Now, if this is the case, then for any two parameter settings, x and y in Rn is the space of parameters, the number of parameters of our neural networks, including the shared and task-specific. We say that x dominates y if and only if f of x is less than or equal to f of y. But this less than or equal to needs to be defined. And so we'll see that graphically in a moment. We say that a point x is Pareto optimal if it's not dominated by any other point. And it's locally Pareto optimal if it's not dominated by any other point in a neighborhood of x. So let's see this. Look at the diagram on the bottom. Well, the points, we have f1 and f2 here. Think of f1 and f2 like the losses of task 1 and task 2. Okay? And we have point C. It's not on the Pareto frontier because it's dominated by configurations A and B. F1 and A and B are not dominated. On the other hand, A and B are not dominated by any other point, and therefore they are on this Pareto frontier. Okay, so now we're looking at this multidimensional notion of a loss rather than just adding the individual terms and summing them with some alpha. We're looking at a high-dimensional space, and we're looking at points. These points represent the parameters of the neural network with the task-specific ones, and we're looking at a Pareto frontier that we want to optimize. For each of ft of x, if it's continually differentiable, then a point X is defined to be Pareto stationary if there exists a set of coefficients alpha in our alpha 1 to alpha t, so alpha is a vector in Rt, such that each alpha is greater than or equal to 0, and they sum to 1. And the sum, the linear combination of the gradients of f of t of x is 0. Just remember how you optimize the function, right? You took the derivative and set it to 0, but here you have a function. Remember, it's a vector-valued function here. This is our function f of x, and you want to find the optimal point. Okay? So we're not finding the optimal point, we're finding the Pareto stationary point, and there is a theorem that says that all Pareto optimal points are Pareto stationary. Okay? So essentially, now let's translate this back to our notation. So what we can do if we have this hard sharing and we share a backbone and we have parameters theta that are divided into theta s for shared parameters and theta t for individual tasks, we can do gradient descent on the task-specific parameters, and we can solve this optimization problem. But let's move this back to from the abstract notation in the first line to the specific notation in the second line. So we're minimizing the coefficients, the weights, alpha 1 to alpha t, and we're summing over all the tasks t, alpha t times the gradient with respect to theta s, the shared parameters, the loss of the individual task t with respect to the shared and task-specific parameters, such that the coefficients sum to 1 and each coefficient is greater than or equal to 0. So this formulation at the bottom, compare this optimization objective that you have on the bottom here to the one that we had earlier, right? This objective. This is called linear scalarization, when you just sum the losses, and this is probably what you have been doing in many problems. And this objective, right? This objective is it's a multi-objective optimization. Okay. But again, this example only handles the case where we are dealing with the shared backbone and specific layers. And there are algorithms, multiple gradient descent algorithms and other algorithms to approximate this and find a solution for this objective. And it is limited. When the Pareto front is concave, it doesn't find those solutions. There are extensions to concavity. There are extensions also to continuous samples on the Pareto front. That's hard parameter sharing. What about soft parameter sharing? Well, in soft parameter sharing, again, we share information in the early layers, but in this backbone, there are also constraints between the parts of the network that we can share. So we might say that the coefficients on the top route have some loss that make them similar to the weights in the center or the weights on the bottom, and we can do some soft sharing or sharing with constraints. Again, there are layers at the beginning and task-specific layers at the end, but instead of just hard sharing and having the same one, we might expand the width of the network there and put some soft constraints, such as similarity between the parameters in theta s, and group them. But then the question becomes, how do you group this? What are these architectures? So, well, you could do ad hoc sharing, take the tasks and compute some relatedness between the tasks, asking how similar are two tasks to each other. And then, based on the similarity between the tasks, group subnetworks within the networks and create a shared backbone that can look something like this. And this has better performance than soft or hard sharing But people would do this manually, fine-tune the networks until they found a good network. Like, even in Tesla, up until a year or two ago, groups of a dozen engineers would ad hoc find such an architecture for multiple tasks, right? And you can think about the problems here. What happens if someone changes or optimizes one thing here, and how does that influence another, etc. This is very ad hoc. And it doesn't scale well. So, well, okay, let's learn this shared architecture. Let's define this shared architecture as a directed acyclic graph. So on the left here, the layer on the top and the layer on the bottom are just the layer on the left and on the right, okay? So I just took this diagram and rotated it 90 degrees clockwise. So this layer on the left and layer on the right are now this top, on the left here, this top and bottom, okay? And now we have, well, we say we have this directed acyclic graph. The nodes are computational operations. The edges are data that's flowing through the network. And we want to learn these connections, the connections in bold. Okay, we want to learn out of all the possible connections here, right? Each node can be connected to every node. What are the nodes that remain? The same way that the ad hoc solution figured out that these should be the nodes. It's like an architecture search. You can see that every node is connected to every other node. And the solution, marked here in bold, learns how to branch, essentially, between nodes in the shared layers. And on the right, you can see more than two adjacent layers. You can see 4 layers there, 3 layers there. And this is essentially what is applied to such a network, starting from all the connections and reaching such a solution. But that solution is optimized by propagating the gradients and differentiating on the branching operation. Another similar work is routing, learning to route. So you see on the left the hard parameter sharing. On the left, you see hard parameter sharing. In the center, you see soft parameter sharing. And on the right, you see a hybrid approach, skipping connections, etc. But it is different than the one that superseded it a year later in 2020. Okay. So how are these evaluated? Well, we need some benchmark to evaluate how well we're doing. And this benchmark can't be a small data set. There is a data set that's a benchmark in the multitask learning field. It contains 4.5 million indoor scenes from 600 buildings, contains 26 diverse tasks. Some of these tasks you can see here, and every image is labeled for all of these tasks. These tasks include, so you see the image on the left, and the tasks include computing the surface normals, the depth, segmentation, and other different tasks. So this is a benchmark data set that you can actually use to run experiments and compare and see which multitask approach or learning algorithm works better. And it's sufficiently large to do these comparisons. Well, the idea when this data set came out was to study the relationship between the transfer between different tasks. So the thought was that maybe we could create a graph that says there are all these tasks, and there's the complete graph from every task to every task. So if there are 26 tasks, n is 26, there's n times n minus 1 over 2 edges in the complete graph. That's a lot of possibilities. So essentially, you create the full graph of edges where each node is a task, and each edge connects task I and j, right? And then you ask, it's 325 edges, and you ask which of these edges, if you do transfer learning from A to B, that really helps. And you get this graph showing the relationships between the tasks as they relate to transfer learning. So this shows that computing the normals helps to do reshading, and also helps to compute the distance, and that makes sense, right? Normals and maybe distance, and there are various tasks here. Also segmentation is important. Computing the normals is important for segmentation, and you get this graph with relationships between tasks, but these relationships, notice, are relationships as they relate to transfer learning, not multitask learning. And an important point to notice here, that in multitask learning, we ask which tasks should and should not be learned together, okay? In one network or different networks. And if we apply multitask learning and take all pairs here for 5 of these 26 tasks in taxonomy and take all pairs, we see, for example, which of these should be learned together? The edges and the normals. And the edges and the semantic segmentation there, it's probably not a good idea to learn them together. And the striking thing here is that if you compare the relationships between learning tasks together in a multitask setting to learning them together for transfer learning, these matrices do not match. Transfer relationships may not predict multitask relationships, and that's an important thing to understand here. Okay, so we need another approach for multitask learning, and that approach that we'll take now, due to Stanley et al., is a combinatorial approach. Okay. So in the combinatorial approach to the problem, we will have a bipart matching of tasks to networks. So here we have an example of 5 tasks and 3 networks. Okay, and these networks, when you combine them, they could be your shared backbone for some some tasks or the other. So this is a hybrid approach. If I were to use match T1 to 1 and T2 to 2 and T3 to 3, and if I had networks 4 and 5 and match it T4 to 4 and T5 to 5, then I would be doing the individual approach, right? If I take each of these networks and clump them together and take each task to be connected to each of them, then I have one for all, right? So somewhere in between, we're looking for a hybrid approach. We're looking to connect this. Well, you can see right away that this is an NP-hard problem. Just connect every task to every network. And now the question becomes, well, which of these edges do we keep and which do we remove? So for example, an approximate solution would be to keep these edges. So for example, network 1 will be used for both task 1 and 2. So network 1 will be the shared backbone for task 1 and 2. This diagram says that 1 is connected to T1 and T2. That means that there is a shared part in 1, and there are also task-specific layers for 1 and 2. Whereas 3 is connected to 4 and 5, but 2 is connected to 3 and also shares some constraints for task 4. Okay? So now the question becomes, how do we find this approximate solution? The tasks are now T1 to Tk, and I'll add a complexity here that we have a budget, which is a budget B, the total time to complete all the tasks. And just to simplify notation, each neural network will be denoted by an integer I, 1 through n. And the cost, the inference cost, would be Cn. So think of the setting where you have your edge device, your mobile device, and you have an image coming into your mobile device, and you have 10 or 20 tasks, and you want a neural network that would do all these tasks in a certain budget, like 15 milliseconds, right? That's really critical when you're working with such edge devices. So we can define the loss for each task, the loss for network N and task I. So for each network we'll have, and a task, we'll have a loss. It would be infinity if the network does not solve that task at all. And the solution S is a subset of the network that together solve the task. So if we have n networks, this is an NP-hard problem because we can choose all subsets, that's 2 to the power of n, subsets, right, of n integers, and we want to choose these connections. So now we can formally define the computational cost of the solution. The cost of a subset S is all the networks in S and summing the cost of each individual network. The loss of a solution on the task is just the lowest loss on the task among all the networks in S. So the loss of S, of the networks in S for a certain task Ti is just a minimum over all the networks in S of the losses of each network on that task Ti that we're looking at. The overall performance of a solution, L of S, is just the sum of the individual losses over all the tasks. And what we want to do is we want to find a solution with the lowest overall loss and cost within a budget B. So we want to find S star such that which is the argmin, given that the cost of S is less than our time budget B and LS. So it's really important to understand that the time constraints are taken into account here, right? If we didn't have a time budget, we can let something run inefficiently and just enumerate all the possibilities until we find something. But you realize here that this is time consuming as well. Someone needed to train all these networks at the first place, right? You needed to have all these networks. And if we're looking at all these networks and training them, that's quite time consuming. So you would do early stopping and train each of the network individually, just a few iterations, and get a sense of the loss for each of the networks. If you have a small number, tens of networks, you can actually get a nice result by matching the tasks on the top. S, D, N, K, E are tasks, segmentation, depth, normal, edge detection, etc., to the networks on the bottom. So this is the combinatorial optimization approach.
Welcome back to our tutorial on meta-learning. I'm Joaquin van Schoren, and in this part we'll talk about meta-learning in the context of learning over a distribution of tasks, so that with each new task we can learn it better and faster. So machine learning, we have a number of tasks. These tasks give us a certain amount of data, and with this data we can learn a model. We need a machine learning algorithm that takes data and some hyperparameters given by the user, and then initializes a number of model parameters, and then given the data, we optimize these parameters so that we get we minimize the loss or we maximize the likelihood of the outputs. Now, if we have a second new task, say running, and if the previous task was walking, we obviously want to transfer information. To learn this new task from scratch would just be unrealistic in the amount of data and compute requirements. And humans can already do this very efficiently. We first learn how to walk, then to run, then to play football, and every new behavior we can learn more efficiently with the more experience we have. So we call this in general bias, some bias we transfer from previous experience. And there's a lot of proof from cognitive science, for instance, that shows that we actually learn these biases. We're not born with them. And humans are also very good at choosing new tasks. Right? We play and we explore and we're curious and we choose new tasks that allow us to learn better in general. So what can we learn? We've seen a trend recently from replacing hand-designed algorithms with learned algorithms. For instance, neural networks, embeddings, we can learn these very efficiently now. And this allows us to think about how far we can go. Can we really go towards general AI generating algorithms that can bootstrap themselves from very simple biases and then choose their own environments and learn better and better. There's a nice paper about this by Jeff Bloom. So this compels us to work on 3 parts. So one is to learn how to learn architectures, hyperparameters, structures, and pipelines, and so on. Once we have an architecture, we can think about, okay, how can we learn the model parameters efficiently? Are there priors or embeddings and so on we can use to do that, and how do we learn these? And the third is, once we have algorithms, what would be interesting new tasks to learn so that we become more general and can learn new tasks better? So in this talk, we'll talk about the second two aspects, and the next talk we'll talk about how to learn architectures and pipelines. So in meta learning, more formally, we want to learn an inductive bias. An inductive bias is simply any assumptions that you give to the learning algorithm separate from the task itself. This could be priors, constraints, representations, model parameters, initializations, optimizers, and so on. Now, important is that this task, so that this bias is minimal in a sense that it should give the right amount of bias to the learner, not too little because then it won't learn faster, not too much because then it will overfit on the previous tasks, right, which we call meta overfitting. One way of doing that is by level optimization. So the idea here is that we take a learning algorithm and we take some aspect of it that we want to learn. For instance, how do we initialize the weights of a neural net? You could parameterize that, express that as a set of meta parameters theta, and then learn these parameters across tasks. Right? So if you have a group of tasks, 1, 2, 3, we want to learn a good initialization, for instance, expressed as these parameters theta. Now, this ends up being a bi-level optimization because these high parameters, these parameters theta, we put them into a learning algorithms, but then the learning algorithms still have to learn on the tasks, right? So say that we initialize a neural net, we still have to learn and fine-tune the model weights. So on the top level, we learn these meta parameters theta, and on the lower level, we learn the per task model parameters phi y. And in this case, we want to learn the optimal set of model parameters phi given the task and the meta parameters we gave to it. The nice part about this approach is that once we have a new task, we can then again imbue the learner with these meta parameters, which we've learned before, but we're also able to then fine-tune further this learner on the new task. This is a bit more in detail. So we learn these meta parameters with a meta learning algorithm. This could be any meta learning algorithm that can, this parametric, right? It needs to express meta parameters theta, which will be the model parameters of this meta model. It has a meta optimizer, F meta, and a meta loss meta. The meta learning algorithm learns these parameters theta, gives them to the base learning algorithms, which will then use them to instantiate models, train on the tasks. This is our inner training loop. And after the model has been trained, we get a final error and we give that back to the meta learner, which then computes a meta loss over a group of tasks. And then uses that loss to optimize its own parameters theta. When it's done like that, when we've done meta training, we can do meta testing, which means we give the optimized parameters theta to the learning algorithm, which can use them to instantiate a model, but is then also able to further fine-tune its own model parameters on the new task. Another way of doing this is with black box models. So these are models which have also high parameters theta, but they are internal. They're not part of the learning algorithm. They're just part of the meta learning algorithm itself. And what the meta learner wants to do is, given a task, given the training data of a task, predict the model parameters which will be ideal for solving that task. Right? So we give the task itself, or at least the training data of the task, to the meta learner, which will then learn an embedding of these tasks, produce a meta model based on a number of hidden parameters theta, get a loss, and then meta train until it finds better internal parameters theta. It gets a signal from predicting the per task parameters phi, And in the learning algorithms, they just feed forward. They just build a learner with the predicted model parameters, and from that obtain a loss, and then the loss over all the different tasks are given to the meta model. So in this case, there's no learning happening on the per tasks, only in the meta learner. When it's done training, it can then make predictions. So if there's a new meta test task, we give again the training data to the meta learner, which will then predict the optimal per task model weights. And then the learning algorithm will again feed forward, use them to build a model, and we're done. So there's no training or fine tuning happening anymore. So we also call these amortized models because there's no training and meta test time. It's also called learning fast by learning slow, because obviously they're fast at predict time, at meta test time, but they're slow at meta train time because they have to learn a lot of times to learn this transformation. This is also related to hypernetworks. So hypernetworks are networks that predict the weights of other networks. And you can see the meta model here as a type of hypernetwork, right? It produces the weights of another network with the clarification that in this case, the embedding for the tasks is learned by the meta learner. Let's see a few examples. So the first example is future learning. So in that case, we are given a number of tasks. So two classes, cats and dogs. And for each class, we have 3 shots, 3 examples. So 3 examples of cats, 3 examples of dogs. That's our training set or support set. And then given a new image in our query set or test set, we then have to classify it only based on these examples. Okay. I will always make it clear when I say training set and test set, I mean the training based test. Otherwise, I'll talk about meta train. That's the collection of tasks, or meta test, the collection of test tasks. Okay, so we can solve this first of all with bi-level optimization. So we have meta learner that, for instance, wants to learn the initial model weights per task. So it learns these, and then the learner learns on each of these tasks, gets the loss, and then over a group of tasks, we combine the loss into a meta loss, which is used to optimize the meta learner. Right? So it learns an initialization of weights. It can also learn an optimizer. It can learn some kind of metric and so on. So we'll see more details soon. Now at test time, we can dispose of the meta learner, and we only need the learned model parameters, meta parameters theta, which we then give to the learner and which it can then use to build a first model and then fine tune that model based on the few examples that it still gets. Right? So it has to learn a model, in this case, on 6 examples only. But because of this initialization, hopefully it can do that efficiently. If we would use a black box model, it's a bit different. So in that case, the meta learner has access to the training tasks. It uses that to learn this transformation between the task, an embedding of the task, and the per task weight 5. And so when this is given, the learner can again feed forward, be instantialized, test it on the test parts of the trained tasks, and then we get a loss, and then we combine that to learn this meta learner. Now at test time, meta test time, we again need the meta learner to produce these per task parameters phi given a new test task. Okay. We can also look at another example for meta reinforcement learning. So in this case, our tasks are these behaviors. For instance, picking an object here and putting it there, or putting an object there and putting it here, or pushing an object or opening a drawer and so on. So for each of these tasks, it can be, the initial state can change, right? So sometimes the initial state is here, sometimes the initial state is there, and that changes the task. At test time, we can either have the same tasks with different initial states, or we can have a new task which is similar, right? Like drawer opening instead of drawer closing, or sweeping instead of pushing, and so on. Otherwise, it remains the same. So the meta learner, the meta reinforcement learning algorithm here, again, has to learn from this theta. In this case, is parameters theta could, for instance, be the weights of the policy network. These could either be fixed, or sometimes you can fix some of them and still learn others. And so when the learning, the RL agent here gets these parameters and has a policy network, it can then construct trajectories, right? So it has learning episodes. It gets initial states, does actions, gets new states. Ultimately, after trajectory, it gets a reward, and then the effective policy, which we obtain, which is modulated on the weights phi, leads to a reward, and that reward we can then transfer to the meta learner, which gets this reward over a number of tasks and is then able to learn the policy for a group of tasks. Or at least learn the parameters phi for that. Again, at test time, we only need the optimized parameters theta to give to the meta learner, to the reinforcement learner, so it can learn effectively on few examples. We can also again do this with a black box model, in which case the meta-RL agent actually has access to the training tasks. So it can engage in a number of train episodes to learn the task and then learn, well, for each new training task, pass the correct parameters phi to the RL agent, which then can learn fast, but because it's given phi, it only needs a few test episodes to learn a task. Learn a policy. At test time, you can again need both the meta-RL algorithm and this can construct the weights for the fast RL agent for solving a particular task. Now, there's a range of different meta learning techniques and different ways to build a taxonomy of them. In this case, we'll use one created by Hospitales et al., where we look at the meta learning algorithm, and like any machine learning algorithm, meta learning algorithm has three components: basically representation, like what do the meta parameters represent, an optimizer to learn these parameters, and an objective to optimize towards. One example is, for instance, to learn the initial set of weights or the initialization of the weights of a neural net. So instead of starting at a random point, a random set of weights, we meta learn what would be a good starting point for our network, so that we only need a few steps of gradient descent to find a really good model. Another approach would be to learn optimizers. In that case, we replace normal backpropagation with a learned optimizer, which can hopefully learn or find a good minima given a few number of updates. There's many more things we can do. We can learn black box models, we can learn embeddings, we can learn high parameters or architectures or losses. Instead of gradient descent, we can use reinforcement learning or evolution. Instead of having this menu of future learning or multi or single tasks. So multi-task is more common. Single task is when you subdivide the task internally. You can have fast adaptation when you want to have a good model after only a few iterations, or if you don't care about that, maybe you want to look only at the performance after 1 million of iterations, or it could be online or offline. There's a whole range of different meta learning techniques that you can build, different applications as well. For now, there's two very good surveys you can read about that on top right here. For now, we'll look at a few key strategies that are good to know about. First, the gradient-based methods. These are exactly as we discussed before. So typically here we want to learn a model initialization phi init. So you can see this as learning a representation that's suitable for many tasks. It's like learning a pre-trained CNN instead of we want to learn all the parameters of the network. Also, with the constraint also that we want to maximize rapid learning. Right? So we want to find an initialization for a group of tasks so that we only need a few gradient descent steps at test time to find a good model. Right? So the fine-tuning should only take a few examples. Now, each task I we give will lead to a task-adapted phi I. And we use the loss based on that to update the meta parameters theta using gradient descent and using an update rule that we can define based on metaparameters theta and the training set. And then after we have learned theta, we can still fine tune it on the test task with the same update rule. The most common, well-known algorithm here is Mammal. So Mammal works by taking a number of tasks, taking an initial set of meta weights, theta, and then we do k steps of gradient descent. So if we start here, we go 1, 2, 3, if k is 3. We find an approximation of the optimal value for that task. And then at that point, we'll look at the test set loss. And then we compute the derivative of the test set loss with respect to theta. Then we update the per task parameters, 5i, as the original starting point, minus a learning rate, alpha, times the gradient that we have observed at that optimal point. Idea being that if we move this way, then hopefully by doing gradient descent again, we'll end up again at a better point in a few number of updates. And then we do this for every task. So in this was a task 1. For task 2, do the same thing. We end up here. We compute the derivative of the test loss here. We have an R phi 2 over here. And then we learn a meta gradient, which is based on the derivative of the test loss for each of the tasks. This is not simply the sum of these because this is a second order gradient. So because we move theta, from here to somewhere else, of course, phi optimal will also change. Right? So we need to back propagate from here all the way back to theta to learn how changes in theta will affect the gradient at the new point. Right? Once you've learned all, this will be a second order gradient that you need to compute. So this will be expensive. At meta test time, after we've learned that, we can, of course, learn very fast. We only need a few steps of gradient descent to then find a phi that's specific to our new test task. This is an example for reinforcement learning. So say that after we've done meta training, we end up with this agent, this AND agent, which has not yet given a goal, right? So the goals could be, for instance, to reach a certain velocity or to move in a certain direction. At time 0, it has only learned a good initialization. So it will just move around a bit. And then after we give it a goal, you can see that it can learn that goal after just one step, right? So if I start this, so you can see, this is just moving according to the learned optimization. And then when we give it a goal, like stay still, it can learn this quite well in a few number of steps. Or if you say move fast, then it can also learn that. So by having initialized this guy, giving it a good starting set of weights, we can then learn with just one update very fast. Right, so this has been a very influential algorithm, and there's many different variations of that. Some of them do things like learning weights per parameter, because obviously in neural nets, some parameters are more important than other ones. And so we can learn different weights for different parameters, which will effectively lead to different learning rates for different parameters, which is reminiscent of many ways to improve gradient descent. We can also do things like curvature and warping, where we change the shape of the loss surface so that at test time, our gradient updates will be very fast, will be better. There's also an online version called Follow the Meta Leader, which works for online tasks. How scalable is this? Well, we have already observed that this is a second order gradient. So this will be quite expensive. Plus it will be very memory intensive because we're learning millions of parameters and we have to backpropagate. So every time we have to learn, we have to store a copy of all the network's weights in memory. So that will be also expensive. So there have been some improvements, or well, not improvements, but faster versions of Mammal. The first one is first order Mammal. And this just replaces this second gradient with the identity function. And what this means is that this update rule now effectively becomes replace theta by the last step in our kth step in gradient descent, right? So if the last step went from here to here, we just copy that, and then the new theta ends up here. Reptile is another approach. So what that does, it says, okay, if the approximation of the optimal for task I is here, we'll just move in that direction. So it's deadly simple. And so it will effectively be 5i star minus theta, and then times a learning rate beta, and then it moves in this direction. And it does this for every task sequentially. So it doesn't wait until n tasks are done. It does this task after task after task. In the first order mammal, the meta gradient is just the sum of the gradients per task. Another way to scale up mammal is called implicit mammal. So instead of doing this backpropagation, what we do is we just use the derivative at the observed maximum phi. This is, of course, this can be bad if phi is far from theta, right? Because the gradient will be very different. So to correct for that, we simply add a penalty based on how far phi is from theta. So if it's very close, we think that we can trust the gradient. If it's very far, we cannot trust it so much, so we have a larger penalty. This leads to this objective. So we add this penalty term with a regularization parameter lambda, just as in rich regression. And this happens to have a closed form solution, so this can be computed much faster. Okay, how generalizable is this? Well, there is first of all a universality proof that tells that mammal is very expressive. It has also been shown to be very resilient to overfitting, especially on small tasks, small test tasks. Other work has found that the effectiveness of mammal is mainly due to feature reuse. And they've shown that by taking the learned parameters theta here in a convolutional neural net and freezing theta for all layers except for the last one, as we only fine tune the last layer. And this turns out to work almost as well as fine tuning all the parameters theta. Right? So this tells us that it's a big part of this ability to learn fast is because it learns a good embedding of the data, basically. Based on that, you can also think about, okay, what happens if we just learn embedding? Right? So it has been shown actually that if you combine the entire meta training set into one big task and you learn embedding on that, then you can still do few-shot learning by using a simple learner, not a neural net anymore, but like a simple linear logistic regression, for instance. And then train this guy on a few examples, and it shows that given a good embedding that you've learned, there are some extra tricks involved, but once you've learned this good embedding, you can actually outperform many of these meta learning techniques. Now, with the caveat that this is only for few-shot learning benchmarks, which admittedly is kind of a special case, right? Because they're all from this very similar distribution. This probably won't work on cases where the test tasks are much less similar to the training tasks. Related to that, it has also been shown in MetaRL that mammal works well, but only for tasks where you only need a few actions at test time. But you can fix that by adding an exploration term to the objective. And this way you can still, this is called e-mammal or exploration mammal, where you force it to actually also learn larger goals at test time, longer term goals. Okay, there's an interesting Bayesian perspective on this as well. So if we view a normal meta learning as such, so we have our meta parameters theta or per task parameters phi, and then we predict x, y given x, right? And this is what we've done before. We sample from the task distribution, we fine tune phi, we produce the test points, and then based on the loss, we update theta, right? And at test time, we get point estimates of prediction. In the base case, ideally, what you would want is an uncertainty of the predictions. If your set of training tasks is very similar, then you can be more certain than when your set of test tasks is very different from each other, right? Or when the test task is very different from your training tasks, again, you would want your predictions to reflect that, right? To have more uncertainty. And so a fully Bayesian approach will be able to do that and produce these kind of predictions. We don't only get an estimate, you also get the uncertainty for that particular task that you want to learn. Now, of course, computing these is intractable, so we need some kind of approximation. One thing you can do is empirical based, so you can fit a point estimate on theta, learn it from the data, and it turns out that you can then express the per task parameters phi as you can factor it as a product of a likelihood and a prior. So the likelihood of y given x and phi, and the prior phi given theta. Right, so you have a likelihood around phi and then a prior around theta. Now, it also turns out that when you use theta here as the initialization of gradient descent with early stopping, so you stop after k steps, this is approximately equivalent to placing a prior over the task-specific parameters. Right? So we know that the optimal point should be somewhere here around phi. And the standard deviation depends on k, the number of steps, and the learning rate. It's actually the case that the smaller k is, the less likely you are overfitting. If you make k very large, then you're more likely to overfit. Now, interestingly, this is exactly what Mammal does. Well, it estimates phi with k steps of gradient descent, and it updates the prior theta to make it easier to optimize phi. So this is a very nice equivalence. Of course, this still doesn't give you uncertain predictions. So to do that, you need a fully Bayesian method learning approach. Right? So to do that, you need some kind of approximate method. So one thing you can do is some solving technique with variational inference. And one example here is platypus, which you see here. And so you can see that given some data points, it learns not only the mean, but also the certainty for all the predictions. There's some other work, that's Bayesian Mammal, and got this one. I think it's amortized Bayesian method learning. You can also use a Laplace approximation, then you get Llama by Aaron Grant. You have variational approximations of the posterior. These are more complicated, but these are called like the neural statistician and neural processes. Now, what if our tasks are not IID, right? So our test tasks are very different from our trained tasks. We can still use this Bayesian approach by using specific latent variables z, and conditioning phi also on z. But this allows us to impose additional structure on it. And there's some very interesting work that shows you that you can actually do this to learn tasks which are very different from what you saw at train time, or somehow different. Okay, a second thing you can do next to learning and initialization is to learn an optimizer, right? So this is a very old idea. It goes back to the 90s. Where there was some work, for instance, by Benju on learning bio-inspired update rules. There was learned from Schmidhuber in '92 about fast weights. So here, the weights of the network are learned by another network that continuously changes the weights of the base network. More recently, there's been work by Hochreiter, for instance, where they replace the update rule with a neural net, right? So phi is phi minus learning rate times some number produced by a neural net given a task. And so we have to learn a set of meta parameters theta, which is exactly what we've been doing before, right? So it's again a gradient-based method, but instead of learning the parameters of theta, we learn parameters of the update rule as theta. A modern version of this was proposed by Andrishevich, which is basically a more scalable version of this LSTM ID, which looks a bit like this at the bottom here. So we have a meta learner that has to learn some parameters of theta, and these parameters theta define an LSTM, which is then used to optimize an optimize model. So the optimize has certain per task parameters phi. The optimizer gets the value, computes the gradient, and returns an update rule. And then does this over and over and over again until we have some test point. We backpropagate through time. We compute the loss. We use a loss to update the meta learner, and that way the meta learner can learn a good set of weights theta to give to the optimizer. So what we're effectively doing is we learn an optimizer that works well on a number of tasks on the same distribution. So the optimizer changes, but the optimizer stays the same and gets updated with new parameters theta over time. This has been shown to work for image classification and also for future learning. But you can also learn other optimizers. First of all, a very interesting finding is that if you look at what these LSTMs and RNNs learn, you can see that they learn something that looks a lot like momentum and gradient clipping and learning rate schedules. For instance, here we can see a learning rate schedule. So you see that's like a warm up and a cool down. These are optimizers for, I think, logistic regression. And so they learn schedules. And here you can see it learns something like learning rate adaptation, right? So if the gradients are small, then you should use a high learning rate. If the gradients are large, you use a small learning rate, which is very similar to what happens, for instance, in RMS prop. Right? But we didn't tell the optimizer to do that. It just learned that from data. There are also RL-based optimizers. It's a nice paper called Learning How to Optimize. So here they learn optimizers for instance, linear models and simple neural nets. And they use reinforcement learning. They use guided policy search to learn a policy to update the weights of, for instance, a linear classifier. You can also add an optimizer to Mammal. So then you do both initialization and optimization in a fully gradient-based way. So for instance, you can do this for learning different learning rates per parameter, as we saw before, where you can learn how to warp the loss surface to get better predictions at test time, or better adaptation at test time. There are also a number of black box optimizers, which typically replace like other black box optimizers, but you learn them on data using an RNN. Okay, for instance, if you would normally use Bayesian optimization to update your hyperparameters, you could also learn how to do that using RNN. It's another interesting piece of work where they have user-defined priors. So if a user can give you some kind of prior, you can give that to, you can learn an optimizer based on the prior. So there's a way of adding bias to a model that you cannot, adding bias to an optimizer that you cannot learn from the data. Another very interesting piece of recent work by Louis Kirsch is how to speed up backpropagation by meta-learning, sparsity, and weight sharing. Right? We all know that sparsity and weight sharing help, but we don't always know how to do weight sharing. So here we just meta-learn how to do weight sharing, and it also seems to work very nicely. Okay, another class of techniques is metric learning. So here what we do is we want to learn an embedding network based on parameterized on theta again, that transforms the input data, detrain and detest. And we learn this embedding across all the tasks, right? So given inputs like flower, bird, we learn an embedding for this. And we do this over a number of tasks. And when we've done that, every input becomes a point in this embedded space. And then you can use very simple models to make predictions. For instance, you can learn a classifier, a linear classifier, to predict between birds and flowers. or you can use something more like KNN-like, where you look at the similarity or distance between points to make a prediction. This can be seen as their own set of approaches called non-parametric approaches. If you squint a bit, you can also see this as a black box model, where this model G conditioned on theta produces these embeddings internally, right, and then predicts the model parameters of, for instance, a linear classifier. But of course, this could also be non-parametric, like KNN. Okay. There's a number of ways to do this. So one simple way would be to use time-based networks. An improvement on that is matching networks. So here, so say we have four classes of dogs here, blue, yellow, orange, and red. And then we have a test example here. And now we want to classify this. So the simplest way of doing this is to learn embedding, right? That embeds these images as a vector. We use the same embedding for a test case, and then we just have some kind of distance function between this one and the ones per training set. Now, the way that this is done in the simplest case, G and F here are the same. They produce the same embedding, and we use a simple cosine similarity between the vectors, and we push it to a softmax to get a probability over all the classes, and then we predict the one with the highest probability. If there is some context, like if the test cases don't come randomly or not IID, we can also learn a contextual embedding, in which case G is the bidirectional LSTM and F is an attentional LSTM. Another approach is very popular are prototypical networks. They're even simpler. So what you do here is you learn embedding that encodes each data point. So each data point becomes a point in this n-dimensional space, depending on how much dimensions you want in your embedding. And then you define a prototype for all the examples of a certain class. Right? So if you have a class C1, we look at all the examples of C1, we see where they are, and then we learn a prototype, which is the average of them. We do the same for class 2, for class 3, and so on. And then at test time, we again embed our test point, and then we see where it's closest to, right? So the class distribution is based on the inverse distance between X and all the prototypes. And again, we define this as a softmax, so we have a probability over all the different classes. The distance function can be any differential distance. For instance, square Euclidean is obvious. And then they use normal log likelihood maximization to learn the embedding. Now, instead of choosing a distance function, which is kind of a heuristic, you could also learn the distance function. That's the idea behind relation networks. So they also start with an embedding of, in this case, the images. So every image becomes an embedded vector. But then instead of saying use Euclidean distance, they learn a distance by first concatenating the vector of each input image with our test image. And then we learn how these images relate to each other. Right? And then this is expressed as a relation network G, which has to learn another set of parameters theta, metaparameters theta. And once we've learned that, we have learned a new distance function. And then the rest is as usual. So you, for each, you just use this parameter, this model G, to then predict which training point is closest to this test point. This is more expressive because you can actually learn nonlinear relationships between the images. Okay, there's quite a few other techniques you can use, like time-based networks. There's also graph neural networks in which every training point is a node, and then there's the edges of weights, so it's fully connected, and there's a propagation rule that then learns the weights between each point. The nice thing here is it's also applicable for semi-supervised and active learning, while all the others are only really applicable to future classification problems or maybe regression problems. Another approach are attentive recurrent comparators. So the main ideas are if you have an image A and image B, instead of comparing them directly with each other, you look at patches. Just as a human would look at certain aspects of the images, it does something like that. It looks at patches and see if these patches match some patches in the other image. So it uses attention and the context. There's also a model called MetaOpNet, and in this case, you learn embedding specifically to then use a linear model to distinguish between classes. Overall, these techniques they're very fast at test time, so they're useful for future classifications. They have fewer applications outside of future learning. And they often fail when the test tasks are more different than the training tasks, right? So they really depend on the similarity. The main reason for that is that they have no way to adapt. I mean, at least with gradient models, gradient-based techniques, we can still adapt. We can fine-tune towards the test task. With method learning, this is not possible. So we're just stuck with whatever we learned at method train time. Okay, a very interesting approach is black box modeling for meta reinforcement learning. So in this case, we have a task. In this case, for instance, we want to pick and place with some certain goal. We have a meta reinforcement learning algorithm that is given training task, and it has time to actually try different things on this train tasks, right? So it's given a large number of tasks, and it learns kind of which policies work well. When it has learned that it can transfer, well, anytime it can transfer a set of weights phi, and these weights phi typically are the weights of a policy network, like an RNN. You give them to an RL agent, which we call a fast RL agent, right? Because it has to learn fast. It only gets a few episodes to train on the train tasks. After a few episodes have been used, we compute the effective policy, right, modulated on phi. And then we can compute the reward, and then we combine the rewards over different tasks, and then we update the meta-RL algorithm, and that way we can learn this. At test time, we then have our trained RL. It looks at test cases, produces phi, and then our fast RL agent can use that to learn fast. If you look at the bottom right here, you see that the training task is here in blue. So you get a starting condition, starting state, initial state. Our agent then has an action, and then every reward and new state updates some hidden parameters. And the agent can do this for a number of episodes. And then after a number of tries, like if it gets 2 tries, it ends after 2 episodes, and you reset the hidden state and you try again on another task. So RNNs basically say these RNNs serve as some dynamic task embedding. So the RNN of the meta-RL algorithm kind of learns an embeddings for these tasks. And then they maximize towards the expected rewards in each trial. This is very expressive, so definitely very powerful. The problem that we still see is that longer horizons are still difficult, typically because RNNs have a limited memory capacity, so it's not easy to learn problems which require many actions. There are some other black box models that try to solve this. They're typically not so easy, so we can't explain them in full. Just to give an overview, there are model augmented neural nets. They use neural tree machines, which are complex networks with short-term and long-term memory and external memory as well. So they're quite complex. There are meta networks. They're a bit more simple. So they have a base learner and a meta learner, and the meta learner has to learn the weights for itself and for the base learner. So this is related to the fast weights ID. And then you have the simple neural attentive meta learner. And this actually directly addresses this problem with RNNs having having limited memory capacity. So what they do is they replace an RNN with a series of 1D convolutions, as you see on the right here. So you can basically choose how much memory you need, and then you can learn either a supervised learning problem or a reinforcement learning problem. Finally, one last thing about training task acquisition. So it's important to realize that what meta-learning actually does is it translates constraints on the learners to constraints on the data, right? So if the learner doesn't learn fast enough, we parameterize some aspect, and then we learn that aspect on the training data. That means that we are limited by how much information that training data can give us, right? So if our training tasks have not enough information, there's not so much we can learn, right? So this is a really good reason to think about, okay, how should we create those training tasks, right? If we can build better training tasks, we can learn much more complex things. So, and the idea is like, can we automatically create new tasks to inform and challenge our meta learners? There's a few bits of research in this area. One is the paired open-ended trailblazer. So that does, it constructs a parameterized environment, so theta e. And by changing these parameters, theta e, we create different environments. Right? And then we likewise parameterize our agents, theta a. And then we select agents that can solve the challenge. Right? So initially, we have one agent and one environment. We train different agents. And then if an agent is good enough, we transfer it to a larger world where we evolve E into E1, E2, E3. And then we transfer this agent. We also generate new agents to learn on this more complex environment. And then when we get agents that are good enough here, we can then evolve our environments. So the idea being that the environments evolve at the pace that the agents themselves evolve, right? That's a very powerful idea. So one problem with this is, you can see it here, so it's a bipedal walker. And basically here it is already pretty good, right? The idea is basically that if the learner gets better, then also the environments become more complex, just to keep it challenged. One problem with the PODE approach is that it has limited expressibility, right? So it is parameterized with theta e. So this puts some limitations on how expressive these environments can be. Of course, you can make theta e very large, and then gives you some more oxygen to work. Instead of that, what you can also use are generative teaching networks. So these are known, for instance, from dataset distillation. So say you have a large data set, you want to construct a smaller data set, which may not make sense to us, but will cause learning to be more efficient. What a generative teaching network does is it learns to generate such data sets, but it also meta-learns the generator, right? So the generator creates tasks for the learner, then we look at the meta loss, and then we use that to update the generator over a number of tasks. So the generator actually learns to create good test problems for a certain given problem. The careful thing is that, of course, that it could generate anything. So we need to be careful that doesn't just generate noise. It needs some grounding in reality. But in any case, these are all very interesting and exciting paths towards the future. Welcome back to our tutorial on meta-learning. I'm Joaquin van Schoren, and in this part, we'll talk about meta-learning for automated machine learning. So just to recap, in the previous part, we discussed how we can learn how to learn algorithms and how we can create new environments. One thing we left open is that in these cases, we kind of assume that the architecture was already fixed. In this part, we'll see how we can also learn the architecture that's ideal for learning the new task. So again, our high-level view, remember that our learning algorithm does not only have model parameters, it also has hyperparameters, which are typically set by the user. I'll use hyperparameters in a very general way, in which I mean the normal hyperparameters, like for instance, the learning rate, but also the neural architecture itself. And if you have a pipeline of operations, for instance, including preprocessing, then this is also part of the hyperparameters. So loosely speaking, it's everything that the user has to decide. So roughly speaking, you can say that when the new task is very similar, you may not need to optimize the hyperparameters. You may just give them fixed and just learn or adapt the model parameters to the new task. However, if the new task is quite different, well, the more different the task is, the more likely it is that we need to adapt the hyperparameters, and maybe we even need to adapt the entire model. As a side note, note that we can also learn the hyperparameters and the model parameters phi at the same time. That's called bi-level optimization. We'll come back to that in a minute. So automated machine learning aims to automate the tasks that humans currently have to do manually. Right. So typically, if you're given a new task, a human expert has to use his or her experience to then decide how to build a number of models, pipelines, or architectures. Then it evaluates those, looks at performance, and then makes another informed guess to build a new model. And this requires a lot of expertise and a lot of time, and it's also often quite tedious, especially when you need to fine-tune some parameters. And sometimes you change a small thing and your performance drops to zero. So it's very tedious to do this kind of work. And AutoML wants to automate this in a data-driven, intelligent, and purposeful way using learning and optimization. So for example, one very typical scenario is that you have to build a machine learning pipeline. You're given some input data, and then you have to preprocess it. You have to extract features. You have to choose learning algorithms. You have to impute missing values, and so on. So all these steps, you need to decide how to do them. On top of that, all of these steps also have their own hyperparameters. For instance, you can have 100 different ways to do feature selection or feature extraction. And yeah, you need to decide how to do that exactly. And on top of that, the architecture of the pipeline itself can change. So you need to optimize both the structure and the hyperparameters of your pipeline. And then you're still not done, because when you then deploy it in real life, your data may change over time. And your hyperparameters, which were optimal before, may have to be re-optimized because the data has changed, or maybe even have to change the pipeline itself. So you can see this is a very large search space, and it requires a lot of expertise to do this well. In neural architecture search, it's a similar problem, which is on graphs. So in this case, you have to decide the architecture of the network. You need to choose which are the layers, the operators you have for each of these. How many nodes do they use? If it's a convolutional net, what are the filter sizes? If it's a deep net, do you need skip connections? Do you need pre-trained layers or transformers, and so on? And on top of that, you also have to decide the other hyperparameters, such as the gradient descent hyperparameters, regularization, batch normalization, dropout, all these decisions. And each of these decisions can have a huge effect on the performance of your model. So AutoML aims to automate all these things using intelligent search algorithms and learning. Now, still, this search space can be huge, right? So your AutoML method may have to spend a lot of time and try hundreds of models, sometimes even tens of thousands of models before it can find a good one. Right? And so the question we want to ask now is, can we do meta learning on this? So can we transfer a bias? Can we learn priors and use meta knowledge, and maybe even use human priors and preferences into a self-learning AutoML system that can then do this much more efficiently, and maybe just after building a few models already find a good model for you to use. As an overview, we'll break this down into three kinds of things we can do. For a larger overview, you can see the survey. And this talk will focus on three typical ways of doing this. First of all, we can learn hyperparameter priors. So if uninformed, we would have a very large, complex hyperparameter space. Remember, hyperparameters plus architectures with pipelines and so on, right? So you want to learn based on which configurations you've tried before, which hyperparameter settings you've tried before, and what the scores were. Put it into a learner, and then the learner has to give you a simpler hyperparameter space, in which it will be much easier to find a good model. Okay? So we want to learn these priors. So which are typically the good things to do, right? Which are the most important things to pay attention to. Right? And if you can learn that, then we only have to learn, search a small subspace of this very complex space. Another thing you can do is warm starting. So instead of starting randomly with a random configuration, like a random architecture, you can learn from experience and start with an architecture or a pipeline that probably worked well on similar tasks, right? So this is related to metric learning. So in this case, we're going to put on the hyperparameter level. So we're going to look at which are similar tasks, and if we find them, maybe we can try the things we tried on that worked well on these similar tasks. And finally, we look at metamodels. These are models that are trained to build entire new models or to learn a certain component, like an activation function. First, I'm going to start with an observation, and that's that current AutoML systems already strongly depend on learned priors that we put into the system. Right? So typically, current AutoML systems are only possible because we have observed certain trends in what makes models work well, and we put that information into the models as a kind of prior. So for instance, if you look at pipelines, there's typically a certain recipe for building a good pipeline. Right? It typically starts with preprocessing. So first you do scaling, then you do model encoding, then imputation, then class balancing or instance balancing. Then you do preprocessing, and then you choose a classifier. And if you're done with that, then you can ensemble or stack multiple classifiers together into a larger model. And so if we know that this is the typical structure of a pipeline, we can put that into a prior that we give to our AutoML system. So we do this typically by fixing the architecture. So we say that this is the only way that you can build a pipeline. There's lots of question marks and open things that we can decide. So on and off switches, you can say. But overall, this is a fixed recipe. So for instance, you can switch on or off rescaling. Or if you do imputation, you can choose between mean and median, for instance. Right? But all of these become options. So you can express this pipeline as a vector, basically, of options. And then the architecture search or the pipeline search just becomes a matter of hyperparameter optimization. We can use any black box technique to then find the optimal pipeline. And this has been done for a lot of the techniques like Autotask Learn, which is a very well-known AutoML method that does something like this, AutoWeka as well, and even like AutoGlue and Tabular, which is a very recent new AutoML system, does this in a very strong way. It has a very strong portfolio of things that it does, like classifiers it builds, and then builds a large stack of them together. So the search phase is even easier, and they don't even do hyperparameter tuning, but they build it very robustly. Now, a question that you may ask, well, maybe we don't need to fix this architecture. Maybe we can learn this from experience. And I think that's totally true. I just haven't seen any work yet that really tries to learn the optimal structure of pipelines from lots of data. The same goes for neural architectures. So we typically have ways to do that. If we have to solve a quite simple problem, we typically stick to just sequential models, and we just select the number of layers, type of layers, and so on, which is good, easy to search, but it's often too simple, right? We can also use some kind of parameterized graph, which is of course more flexible, but it will be harder to search. Now, what we've seen from well-performing models is that they tend to have a repeated motive structure. We call them cells. For instance, if you look at inception, you can see it starts with input and stemming, and then it has 4 of these inception cells, then a reduction cell, and then 7 of these inception cells, and then again there's a reduction cell, and so on. So these cells are repeated, right? And that apparently makes models work well. So let's use that as a prior. So, and this is called the cell search space. So we assume a microarchitecture in which is just linear. It's just a sequence of cells, right? Just as we saw here at the bottom. Right? And then the only thing we need to do is to learn these cells. And this drastically makes the problem simpler. It's a perfect example of compositionality. Right? We break the hard problem down into smaller problems and we solve the smaller problems much easier. Yeah. So this makes the search space much smaller. And also these cells, they can be learned at small subsets of the data. You don't have to always evaluate the entire network on the entire data set. We can test these small cells on smaller sets of data. Now, this doesn't pose a strong domain prior. Now, it has been shown that this works very well for most vision tasks, but of course, this won't work well for other tasks. And here again, the question is, okay, we've observed this and we use this, but maybe there are other structures, hierarchies, ways to compose neural nets that we haven't discovered yet, and that maybe we may want to learn. And so one case where the cell search space was effectively used was with NASNet in 2018. So there we learned these cells using a reinforcement learning-based search algorithm. So it starts with some hidden state, which is some kind of input, and then it decides to add things like a pooling layer, convolution layer, that adds them together, ends up with a new state, and then we choose a new state, we add more layers and so on. And after a while, we find certain cells, like this is a normal cell, and here is a reduction cell, and we train this on our data. Now, this got state-of-the-art results in ImageNet, but it was quite expensive. It used over 450 GPUs for 3 to 4 days. And this was even a cheaper version of an even more expensive version before. You can also use this in neuroevolution. So AmoebaNet, which is also one of the state-of-the-art ones in 2019 for ImageNet, did the same thing, but just used neuroevolution instead of reinforcement learning. And again, found new cells that worked very well for image classification. Interestingly, shortly afterwards, it was also shown that you can get equally good results using multi-fidelity random search. This is a random search in which you don't evaluate every random model on every full data set, but you evaluate many random ones on a small portion of the data set, and only the ones that work well on a small portion of the data set you try on large data sets and so on. And apparently they got very good results just doing that. So this tells us that a lot of the power lies in the cell search space. It is a very strong, useful prior for these types of tasks. Another interesting prior is weight sharing. And this is taken to the extreme in these weight agnostic neural networks, to the extent that all the weights are shared, right? So all the weights in the network are the same. And the only thing you do is to learn the architecture. There are extra biases, like there's a minimal description length, which means that like you prefer smaller networks over large networks. And there's also probably this Baldwin effect in evolution. So if evolution discovers a certain like submodule that's interesting, this sort of survives and gets spread out to other candidates and so on. But still, it's quite amazing that they can build working models without learning any weights. That's again gives us some indication that weight sharing is really, really important. So they've tried this for reinforcement learning tasks like this bipedal walker and this race car, which worked very nicely. You could inference, they've shown that you could also do this for image classification, but this tends to become very complex. It's not rediscovering convolutions in any way. Okay, now, first thing we're going to do for meta learning is to see whether we can learn these hyperparameter priors. One thing you can do, for instance, so assume that you want to use a black box model, a black box optimizer, like Bayesian optimization or evolution. You may want to reduce the number of hyperparameters that you need to tune. And so what you can do is you can change the values for all the possible hyperparameters and see what the effect is of that change on performance. If changing a hyperparameter gives you a big effect on performance, then this hyperparameter is possibly important. And that's the idea behind this functional ANOVA approach. And so you can see that they've done this for all kinds of hyperparameters of neural nets. And from this, you can see which ones are likely more interesting to tune and which ones you may just leave at default and not touch. Follow-up work on that also said, well, this is true, but if you have a good default, then you may have, then changing it doesn't make sense, right? So what you do here is, first of all, you learn good defaults, which is an art in itself. After you find those, you then see, okay, how much can we still improve over this learned default, right? And then you can establish a tuning risk. For instance, here you see for perfecting machines like C and gamma have a pretty high risk, while tolerance and string have very low risk, for instance. Okay, now a short interlude about Bayesian optimization, because this will be very useful in certain ways. Bayesian optimization is a technique to optimize the hyperparameters. Typically, these hyperparameters are all numeric. What you do is, say you have 10 hyperparameters, so you have 10-dimensional space to search. Now imagine you only look at one, right? So say we have one parameter, for instance, the learning rate, right? So in this graph here. So what we do, we start off with randomly choosing a number of learning rates, right? And we evaluate those, and then we see a performance. So this is the first one, it gets this performance. This is the second one, it gets a higher performance. Okay, now we want to know which other learning rates may be better. So we fit a linear regression, a probabilistic regression function to these points, hoping that this will allow us to predict which other learning rates are going to be working well. Now, of course, if we just use a normal regression function, we will run to local minimum. So what we will do instead is this combination of an acquisition function and our model. So our model has to be probabilistic, so it gives us a mean and an uncertainty. And the acquisition function weighs off both. So it wants to give us a point where we have high expected performance, but also high uncertainty. And there are different acquisition functions you can use. The most commonly used one is expected improvement. Okay, once you have found this interesting point, you evaluate it. And you try this hyperparameter on your test data, and you'll get a new point here. And then you refit your surrogate model. The surrogate model is the name for this regression model that we fit to data points. Then we recompute the acquisition function. We have a new point, we evaluate that, and we continue. This is a very nice method. It has very nice guarantees that it will find a good optimum in a limited amount of time. It works in all kinds of situations, and it was used in the original AlphaGo to tune the hyperparameters of the multicolored tree search that they used in there. Okay, now besides from being a good way to optimize black box problems, there is the model itself encodes information about the hyperparameters, right? And that's something that we can really use. First way, not a first way temporally, but a very interesting way to do this is this learning of a basis expansion. So what you do here, so instead of learning this complex, expensive Gaussian process surrogate, remember Gaussian processes are cubic in the number of points and dimensions. So doing this for a very large search space becomes very expensive. So what you can do, you can use some kind of meta learning here. So given a large number of configurations and scores, you can put this into a neural net to then learn a basis expansion. So what this does, it learns basically. So if you have a hyperparameter here which behaves exponentially, well, then we just take the log. Or if it behaves like a sine wave, we replace with a sine wave, whatever. So we learn a basis expansion that transforms this hyperparameter search space into one which we can model with linear models, right? So this will be a higher dimensional space, right? So we take our lower dimensional space and we construct a higher dimensional space in which we can fit these hyperparameters with a Bayesian linear circuit. It's great because now we can do it very fast, and we have learned a very nice, we've learned the relationship between the hyperparameters. We can also transfer the circuit models themselves, and that becomes interesting when we have a new task. Right? So say we have built the circuit models for a number of tasks in the past, and now we're given a new task. Well, we don't know whether this task is somehow similar to the other tasks, but we assume that this information is still somehow useful. So what we do is we take the sum of all the circuit models on previous tasks, which gives us a new circuit model S here, and we use that to tell us which hyperparameter may be useful. After we've done that, we evaluate that, and then we see, okay, which circuit models were actually right, and then the ones which were right are given a higher weight. And so by doing this, by testing different configurations on your new test task, you learn these weights, and you learn how to combine the different circuit models. In rough terms, this means that you learn which tasks were similar in terms of whether the hyperparameters behave the same way on your new task as they did in the previous tasks. Right? So this is a very nice way to use this information. So you're not starting blind. You're actually starting from what worked in the past, and at the same time, you're learning how this task is related to prior tasks. Some other follow-up work, which looks very similar to what we discussed in the previous lecture on meta-learning. So in this case, remember we had these different algorithms. So here for every algorithm and for every task, we build a circuit model. And the reason we do this per task and per algorithm is because then the circuit models become simpler and are more likely to transfer well. So if you then are given a new task, again, we build a linear combination of all these prior tasks and the new task. And then we evaluate those on the new task, and then we learn these weights as before. And that way we can, again, have a new super surrogate that we can use to tell us which hyperparameters will work well on a new task. Okay, another thing we can do is warm starting. So the idea is here that instead of starting from a random neural architecture or a random pipeline, we start from ones which have been shown to work well in the past. Now, this requires us to have some measure of similarity between tasks, right? Because we want to reuse pipelines and architectures from similar tasks, but not from totally different tasks. So you need a way to establish similarity between tasks. There's a huge number of ways to do that. A lot of this work was done just in the last year. So for a long time, we were using these hand-designed statistical meta features, which get you they're useful and they get you some part of the way. But recently, we have also been looking at how we can actually learn good task embeddings. And there's different ways to do that. So first of all, there's task2vec, which is a task embedding for image data, which works with a probing network. So you push the data through a network and you look at the response, and then you put it into the efficient information matrix, which then gives you a kind of embedding for image data. You can use optimal transport, which is shown here at the bottom. So say there's A of digits, here there's a B of clothes. You want to see how similar they are, and you compute a similarity measure based on comparing probability distributions of these two tasks, two data sets. You can also construct metadata embedding based on a textual data set description. So if data has a textual description, you can push this through a transformer, build a text embedding, and then you can use that to measure some different distance between data sets. There's also dataset to vec. This one looks at batches of data sets, which kind of solves the problem of having data sets of different sizes, and then intelligently combines those into a vector that you can then use to measure distances between tasks. And there's also this distribution-based invariant deep networks, which also learn some kind of embedding of the tasks. Okay. So this is all very new work. There is no data yet on which one works better or how to combine these in certain ways, but it gives us some oxygen to do work in this area. Okay, so how can we use these task embeddings? So one thing we can do is kind of a K-NAN approach, which has been very successful for a very long time. So what you do is, given a new task, you kind of see which prior tasks in memory are similar to my new task, and then I just use the pipelines or the architecture that worked well on those similar tasks. So for instance, Autocycled Learn does this. So if you give a new task, it has this memory of over 500 OpenML tasks, and then the best pipelines on these tasks. And when you give a new task, it just looks up which were the good pipelines and then starts the search with those. So it uses Bayesian optimization, but instead of starting Bayesian optimization randomly, it starts with pipelines that worked well before. And that gives a very substantial boost. And because of this, it also won several ITML challenges. Another thing you can do is probabilistic matrix factorization. So here you learn embedding for both tasks and configurations. So imagine that you have scores. You've evaluated different configurations, different pipelines, different architectures on different tasks, and you put them into this big matrix here. And you see the scores of a configuration as kind of a rating, right? If you remember how the filtering works. This ends up being a sparse matrix where for every task and every configuration, you get a score. And then you learn latent representation using matrix decomposition, probabilistic matrix factorization in this case, which will give you a latent representation of your configurations and your tasks. Right? So if in this case we look at the latent description of these configurations, we can see every dot here is one pipeline, and we can see which pipelines are good, they cluster together, which pipelines are bad, they cluster together. So this latent representation gives you some information about how configurations compare to each other. And you can actually use that to then build a new search space. Right? So instead of having maybe 1,000 possible hyperparameters, you can learn a lower dimensional latent space, in which is easier to model how these hyperparameters behave. Another segue now is about DARTS, which is a technique for differentiable neural architecture search. So the way it starts with one-shot model. So it's a fixed structure for your neural net, and the user has to provide this, right? So it consists of a number of states with gaps in between, and you can fill in these gaps with layers, for instance, a convolution layer, max pooling, or do nothing. Okay, and this creates a space of possible neural networks. Then you learn this through bi-level optimization. So you give each of these links here a weight alpha. Then you try some of these weights on small part of the data. You get the score back and use the score to then update the weights alpha. Then you use that to do another mini batch updates the model weights. So you optimize the model weights and these weights alpha at the same time. So it's a kind of bi-level optimization. And through doing that, you converge into a file network. One thing you could do is you could warm start DARTs. So instead of starting from this use to find one, we can learn a good model to start from. So in this case, we looked at different architectures learned at different data sets. And these were all image classification data sets. And from that, we built this initial model. So this has a number of states for our cells. And between them, we have options like max pool, average pooling, skip connect, and so on. Okay. So we learned this based on previous trained models. And then we can then use that as input for darts. And then we can learn and find good architectures much more efficiently. Right? So here results for aircraft and words. Right? So you can train this initial model on one data set and transfer it to other data sets. Last part are metamodels. So these are models that explicitly you use to build entire models or components of the model. The oldest technique here comes from algorithm selection, which has been done for a long time. And you can build different models. They don't build entire pipelines or architectures, but they help you make certain decisions. So for instance, you can have zero-shot models which predict the best configuration given some meta features, right? So you have your data set, you measure some things about the task embedding, right? So you give the task embedding then to the meta learner, which will then tell you which is the best algorithm to choose, for instance, or which is the best imputation method to use, or which is the best feature selection to use. Right? So you can train these meta learners to answer these kind of questions. You can do the same thing with ranking models. If you were interested in the ranking of possible classifiers, you can do it as well. You can see which algorithms configurations you should consider, which one you should tune, yes or no. Or you can even predict runtime. And this happens to be quite doable. So if you want to search a large space of possible models, you could train such a meta learner to tell you which ones are going to be fast, which ones are going to be slow. And you could use that, for instance, to pay more attention to the fast ones first before you're going to put really serious effort into also evaluating the slower networks or the slower pipelines. You can also learn model components. Like you can actually learn nonlinearities like activation functions. So in this work, so you used a reinforcement learning based search over a space of likely useful activation functions. So they did things like having, in this case, like a logit function, multiplications, sine waves, whatever. So they built a search space of possible functions, and then they searched that to see which activation function actually performs well on a group of tasks. Right? And there's some interesting results there. For instance, they discovered this swish activation function, which has been shown to outperform ReLU on this group of tasks that they had. You can also learn optimizers. So an optimizer is basically just an update rule. And so you can use reinforcement learning based search or other techniques to search the space of possible update rules. So again, you define a search space with a number of components of update rules. So obviously like the gradient should be in there, but you can combine it with other things as well. And so if you do that, you can learn new optimizers, for instance, the power sign here, which is defined as the exponent of the sine of the gradient times the sine of the moving average times the gradient. And they've shown that this actually works better than Atom or MRMS-prop. But the more general message here is that you could learn these things, which is interesting because you then don't have to decide what to do. You just learn the best optimizer and the best linearity for your task. Or vice versa, it could be interesting to just learn these on a bunch of tasks and then discover new things like these functions and then reason backwards, okay, why would this work? This could also inform us how to do better machine learning. And lastly, you could also use this to learn acquisition functions for Bayesian optimization, which are more robust. Okay, another interesting technique you can use here is multicolored tree search and reinforcement learning. And this is a method called AlphaD3M. There's also one called Mosaic. And this operates through self-play. So in this case, you have a multicolored tree search which generates pipelines. So this doesn't work for architectures, but it works for pipelines. So every path in this tree here is a pipeline. You give the pipeline, you evaluate it, and you give it to a neural net. The neural net here is an RNN that has to predict action probabilities. So these are things like adding a component or removing a component from the pipeline. And it gives these action probabilities to the multicolored tree search, which will then use that to sample the next pipeline to train. You also give the activation, the evaluation of the pipelines, and the neural network also has to predict how well a pipeline will behave. Okay. Now, because this tends to end up producing a lot of bogus pipelines, you want a grammar as well to avoid invalid pipelines. So once you have this, you can just do self-play, right? You can keep this running over and over and over and over again until the network learns how to build good pipelines for a new task. And the nice thing is then after you've trained this on one task, you can keep the weights and then try it on a new task. And then hopefully that will thus give you good initialization for solving the new task faster. There's also neural architecture transfer learning. So in this case, we have a task embedding, like a source task, and then we feed it into an RNN, which then has to, so an RNN controller, and this will then produce, actions. So you're building in a reinforcement learning agent. And there's prior information from this previous task. So which was a prior task, which were the prior actions, giving that to your RL agent allows it to learn this new RL controller faster. Well, the controller aims to learn the agent faster. In this work, we use meta-reinforcement learning for neural architecture search. So the goal here is to build a model for image classification through neural architecture to meta-reinforcement learning. So what we do is we train an agent. What the agent has to do is certain actions like adding a convolution layer at some part in the network. And you do that through these neural codes. So every neural code is a certain action that you do, like adding something or removing something from the network. And then you train the agent to learn how to do this. So you train an agent how to build a neural network for a certain image classification task. And what this gives you is that, well, of course, in the beginning, this is going to be very expensive because, well, RL agents don't learn that fast. And evaluating that is expensive. So you will have to spend a lot of time in the beginning to train this agent. But after you've done that, you can transfer, it has learned how to do that. And so if you give the new task, it can actually effectively transfer the information and learn the new task faster. And so what we see here is we have 3 of these image classification data sets, like Omniglot, which is quite simple, Flower, which is more complex, and DDT, which is about textures, that's even harder. And so after the first task, we see that, well, we are the blue ones here, MetaRel. MetaRel doesn't do much better than just a DQN reinforcement learner because, well, it has no extra benefit over it, of course. But because it can transfer, because it's a meta-reinforcement learner, you can transfer to a new task. And at the new task, you see it already starts outperforming the DQN. At the third task, it becomes very apparent. Also interesting to see is that if you look at the policy entropy, is that for the first task, well, the entropy is still quite high, and only at the end it lowers a bit. And then if it goes to the second task, you see that it immediately drops. So it uses information from the previous task to learn this new task faster. And then when it gets to the new task, which is harder, first the entropy increases because this task is quite very different from what we saw before. And then it learns how to solve the task as well. So you can see there's definitely a transfer of information across tasks. And finally, meta-analysis. This is a nice method that combines Mammal with neural architecture search. And in actuality, it combines reptile with darts. So remember reptile from a previous part of this tutorial. So there we use gradient-based meta-learning to learn a good initialization for a network. And remember that darts wants to learn this connection weights alpha, right? And so you can train both of them at the same time. And so you basically have, this is just, this image here is simply mammal, but in a different representation, different structure. And basically what we do, every time we have to update the weights or the meta weights, we also update the weights of darts. Right? And by doing those two at the same time, we end up with a method that can do fusion learning, but also learns to build the best neural nets for doing that. Okay, with that, we've become full circle with the previous lecture, previous part. Thank you for your attention and see you in the next part.
Applications are abundant. In automated machine learning, we've seen various applications. In computer vision, learning from small data. And we've talked about the few-shot approach. In robotics, learning just from a few examples and generalizing. Whether you pick up this water cup or another cup, or these are different. In natural language processing and cross-lingual generalization, does it help when we know multiple languages to learn language number 101 if we're training something that already knows 100 languages? Or in machine translation, in mobile data analysis, think about billions of people or millions of people having data on their mobile phones. Each of these can be considered a task, and each user has its own data, but learning from one user's data, well, we have millions of people. Each of these millions of people is a task and its data, and then meta-learning algorithms can be used to learn from everyone's data efficiently. Essentially, the grouping here into individual data and tasks are straightforward. They're just individual people. And so think about all the data that you create, whether it's on mobile devices or other devices, that's a data and task. And if we have data and task from many, many people, then that's the setting of meta-learning. So there are wide applications here. Discovering physics formulas. We've talked about learning from data and learning to learn from data. This is symbolic representations. And in education, answering and generating math questions. And what we're looking at is a special case of learning to learn courses. Learning to code, combinatorial optimization, and autonomous vehicles as well. In supervised learning, we have labeled data, like the data we saw here, a learning algorithm, and a predictor. And we said, well, if we look at these models that have these losses, they're end-to-end, they take the data in a supervised setting, they're not using RL, they can go pretty far. But let's see if we can replace these building blocks with this architecture with other things. We know that we can add unlabeled data to labeled data and improve. And the amount of unlabeled data that we have is orders of magnitude more than the amount of labeled data. So instead of taking a ResNet that was trained, pre-trained on labeled data, we took ResNets that were semi-supervised, trained on billions of unlabeled example. So essentially, that's the first thing. The second thing is we usually use these ResNets, these pre-trained models, by transfer learning. We take the source data, the target data, and the source and target data have different distributions. The target data labels may not be available. And usually what we do when we use ResNets, we do transfer learning. So we said, okay, we can do transfer learning with these semi-supervised models. So the question was, in the real world setting, in the application of self-driving vehicles, would using semi-supervised models work both for low-level representations, inputs and outputs, and for mid-level representations, inputs and outputs? So we looked at two data sets. One had low-level inputs, as is shown on the left. The inputs were just images from the camera, and the outputs was just steering angle and speed. That's the left column. And another data set called New Scenes had these mid-level representations that you just saw in the various examples. New Scenes actually has scenes from the Boston area. So this is data from around here. And the output is trajectories shown here by these lines. What looks like feathers, these are trajectories and probabilities over trajectories that we can predict. And so we have two architectures, one on the right for low-level inputs and outputs, and one on the left for mid-level representations, inputs and outputs. The one on the right with a pre-trained ResNet won the ICCV 2019 Learning to Drive Challenge in 2019, a year ago. We replaced the ResNet, the pre-trained ResNet that was trained on supervised examples, with a semi-supervised model that was trained on billions of unlabeled images plus the supervised examples. And also replaced the ResNet on the left part of the architecture with a semi-supervised ResNet. So essentially, we took these two architectures, kept everything the same, but just changed the building block of this ResNet. Instead of plugging in a supervised ResNet, plugged in a semi-supervised ResNet. So essentially what we're doing is, instead of taking data that is labeled, where each of these dots have a label, we're looking at much more data, many more dots on the manifold, both in the input and the output spaces. And essentially, taking unlabeled data is very useful to improve results. That was the hypothesis. And the comprehensive comparison of the available supervised and semi-supervised models shows that this hypothesis is correct. If you compare a pre-trained supervised ResNet 50 with a semi-supervised ResNet 50, then the results are better, here shown in bold. The first column, lower is better, and in these columns, and you can see that the semi-supervised models perform the same, all within exactly the same architecture. So we're just replacing one box, and they perform the same across the board, whether you use a low-level to low-level representation or a mid-level to mid-level representation. So our conclusion was that given the same network system and the same computation time, if you just replace those CNNs and models with semi-supervised models, they will outperform the supervised models in the real world, both in mid-level and lower-level representations. And I think this is important because this shows that in the real world, in real-world applications, you can now use semi-supervised models. But now the question becomes, how do you even get to these mid-level representations? Well, we know that this is a multitask learning problem. We know that in order to get all these 3D bounding boxes for this mid-level representation, you need to perform, say, 100 tasks. And this is the tasks that the Tesla autopilot performs, and each of these tasks might have subtasks. So in order to get to that nice mid-level representation that you can feed into the architecture which contains these boxes and performs well, you need to actually perform multiple tasks. And then the question becomes, how do you perform these tasks? Using the same network, using a different network for each one, using a shared backbone, etc. And I think this is a problem we saw at the beginning. We said, okay, if we have these tasks, T1, T2, T3, 4, 5, and there are 100 different tasks to get these mid-level representations, and we have various networks that perform for each task, this is a combinatorial optimization problem, which is a bipart matching of tasks to networks. So this is an NP-hard problem, which network to use for which task, but we can find an approximate solution to understand which tasks should be learned together. OpenAI built GPT-3 and built that from transformers. Let's use GPT-3 and transformers as a building block to the next level. We want a chatbot that would be very convincing in real-world application. So how can we build a chatbot from transformers? Well, there is user input, and when we have a chat, we take turns, and there is a dialogue. And so we need to understand the user input. We need some natural language understanding. We need to track the state of the dialogue. Each person is taking turns, unless they're debating like yesterday. They are taking turns politely discussing. Then there is some policy learning, and eventually one responds to the other, and the system gives an output. Okay, so this is a turn-based dialogue. So first of all, we can think of the input of the user and ask, what is the goal of our chatbot? Is the goal of the chatbot just to socialize? Is the goal to perform a task or to answer a question? And those two goals are pretty different, but first thing is to understand what's the intent. Is the intent of the user to make conversation? Is it talking to Alexa to make conversation? Probably not. Probably wants to do something, or is it ordering something online or something else? And then there's first understanding the intent, or modeling the intent and saying whether this is goal-oriented, or whether we have a task in mind, or whether this is an open question, yes, no, agreed, thank you, or socializing. So we can now map the entire dialogue history to the state of the chatbot and map the user intent and the state to an action. So the student asks, tell me about the meta-learning course. The chatbot understands that the task is inquiring, and the action it takes is providing facts. And we have a dialogue policy learning system that takes the action of providing facts. And finally, the fourth system, a natural language generation system that maps that action of providing facts to an actual generated sentence output. So we have an input, tell me about the meta-learning course. We identify the intent, we take an action, and taking that action amounts to outputting a sentence. Okay. The problem with this is that we've just broken down our chatbot into 4 components. We've said that the chatbot has a natural language understanding component, 1, followed by dialogue state tracking, 2, followed by a policy learning, 3, followed by a natural language generation. So this maps the input to the state, and this one maps the input and the state to the action, and this one results in the output. And this takes turns, right? And each of these is a system. And if we put this as a pipeline with 4 parts, then that would probably be very difficult. It would probably be difficult to update. It would require an expert to be involved and a lot of annotation for every one of these 4 parts. For understanding the input, tracking the state, predicting the next action to take, and translating the action to the sentence to answer. But this is how chatbots were built just a few years ago. Then came in language models, and language models supposedly are end-to-end. You have a user input and you have a system output. But what are the limitations here? Well, there's no explainability. You don't know why this happened. You can't control it unless you put some mechanism of control, right? And you need a large training corpus for every single task. Okay, so a solution was, let's share the backbone of the transformer for all these 4 tasks. So we have the 4 tasks. The 4 tasks are natural language understanding, mapping from the input to the state. And then the next component is dialogue state tracking. So we have our input, we have our state. The next component is policy learning, we have our action, and the next component is language generation, is generating our output. But all of them will share the same encoder. So we'll share our GPT model, and we'll have, this would be our GPT, our transformer, and we know that we can build the transformer such that it performs different tasks. So the different tasks will be these 4 tasks. You'll share the backbone, and we'll have different decoders, one for each of these tasks, and pass information between them. So we'll use the same encoder, the same transformer. Then we'll decode the input to the first decoder, the NLU, pass that on to the DST, decode to the DST. We can also use a database like ConceptNet here. Then decode the DPL, the action, and then decode the NLG, the output. And this is how a modern chatbot is built, on the same transformer, on the same backbone. It's a multitask learning, essentially. So a chatbot has multiple tasks, and the 4 tasks are defined here, right? They're defined by state, action, output, where ST is the dialogue state, AT is the system action. We have a summary of the previous time step, of the previous state and action. We have an output of the previous step and the system input. Okay, so as an example, the user intent is a greeting. The NLU component understands that. Then the dialogue history, there is none. We just started the dialogue. The system intent to respond, the action that the system takes. So this is the user input. This is a system intent. The action is to greet. And then the system output of the natural language generation is saying, I'm fine. Okay, 4 tasks, 4 equations, almost like a round of reinforcement learning. Okay, on a single shared backbone. So the advantage is it's explainable. You can do complex tasks. You can control each of these modules for a specific task. But again, you can surprise this chatbot, ask it things that it's not trained on, and it would respond. The generation module can respond in various ways that you want to avoid. It might say things that you want it not to say, etc. So you might control the language generation part and say, okay, here are constraints on the natural language generation part, on that model. You won't allow it to output certain text. That doesn't capture the strategy in between the conversation. And the conversation is a multi-turn dialogue. And when humans have a dialogue, they start building a repertoire of some repertoire of interaction back and forth between the person they're having the dialogue with. And so you'd like a sequence of strategies using strategies that people use when they have a dialogue. For example, using credibility, emotion, logic, self-modeling, a personal story or information. If you first act with credibility, and then self-modeling, and then tell a story, and then add information, and then emotion, and then you would get the desired result, right? That could be a sequence for your task. So you can take a lot of data and see which data actually leads to the result you want to achieve. In addition, if you add to that personalization, if you know the age, gender, interests of the user you're interacting with, you even improve performance. At the end of the day, this is the performance of a chatbot, where a chatbot's goal was to persuade a human to give money. In a real world setting, real money, real setting. And the chatbot was better at getting money or donations from users than a marketeer, than the human. So the baseline is 32% success. Then we see the multitask at 37. The multitask plus adding imitation is 47, plus adding strategy history is 51. The human is at 54%, and adding the background information from the user, knowing your age, gender, interests, is at 59.7%. It's actually better than humans at a task of getting donations for a real cause. And this was done on a real-world, large-scale experiment. Now let's look at challenges. Raven's Progressive Matrices is a booklet of 60 puzzles like this, okay? So you have more than one puzzle. You have 60 different puzzles that are similar but different. They could do transformations. They can change the number of edges. They can scale. They can color. The transformations differ, but the setting is that instead of just one puzzle, you have 60 different puzzles. What is the solution, and how would you devise an algorithm for solving this problem? Why is 3 the solution? Each image on the left has a left side and right side. And then each part is made up of a building block, and that building block either undergoes a transformation or not. The side on the left doesn't, and the side on the right does. So essentially, the problem here, okay, so in this case, these are the building blocks, A, B, and C, right? 3 building blocks. And then the left is the building block, and the right is the block rotated and mirrored, okay? So there's some transformation on the left, and the right is just rotation and mirror of the same building block. So essentially, here we are jointly inferring 2 things. You can call this the hidden attributes and the pattern, or the building blocks and the transformation, and or the alphabet and the composition rules. That's what makes it seem hard, because you're jointly figuring out what's the alphabet and how to compose the letters. How would you go about an algorithm that would solve this? This problem was tackled in 2019 and 2020 by the vision communities, and they looked at this as a multitask learning problem, where you have each of the problems. In this case, the outputs were 8 possibilities and the inputs were 8 possibilities, so it was a harder problem. You had 8 inputs, you needed to predict number 9, and the output was 8. Just to make it, instead of 1 to 6, you had 1 to 8, just to make it uniform. And so you can stack the 8 frames of each individual, segment each individual puzzle into 9 pieces, take the 8 known contexts that you know, right? All the images that you know, the sub-images that you know, except the one that's missing from the input, all the sub-images for the output, and consider each one a task. 8 input images, 1 output image. 8 input images mapping to 1 output. And then you have 60 problems. For each problem, you have 8 such mappings, and then an encoder, fully connected layer, softmax, and you learn all these tasks. And you break this down into multiple tasks, and that already performs better than human. Okay, this is the REL base. Okay, just to say, okay, multitask learning, right? Just break this into multiple tasks, and what is the unit of the task? That's already better than human. And then a tweak on that is encoding the scale and the positions of the objects, and that's even better. Is already at superhuman level. And I would call this an example of multitask learning where you can actually break this down into many, many tasks. Multitask learning has been used for protein function prediction in the past 2 years. Specifically, when you like to predict function, you can either go through structure or you can go from sequence directly. And if you'd like to predict function, for example, whether this is an enzyme or not, or other different functions, then you might as well use a shared backbone to predict all the different functions, and rather than have a network for each task. You can use a multitask framework where you have either a shared backbone or just a decoder for each of the tasks, and that's highly beneficial to train on all of the functions rather than train a specialized network for a specific function. Let's start with a simple exercise. Here is function 1. What is lug and what is fep? And the word dax. So lug and dax are blue and red, and what is fep? 3 dots. So fep is not the color, it's the number, and lug and dax are the color, blue and red. Okay, so this is one function, a set of rules. Here's another one. So what is with and what is blicket? Lug blicket with is blue, green, blue, and with blicket dax is green, red, green. So blicket is what here? So blicket is surrounds. And what is with? Well, with is green. So lug blicket with is blue around green, with blicket dax is green around red. Okay, this is a second function. Let's do a third function. So the third function is lug kiki with. So we know that lug kiki with. We know that what lug is and with and dax are. What is kiki? To replace lug and with blue and green, and dax and lug with red and blue follows. So blue follows green, red follows blue. Great, function 3. And so the primitives that you learned here could be dax, which is red, with it, which is green, lug, which is blue, and zup, which is yellow. Okay. Now let's see if you learned the language and how well you've learned the language. So now please apply the language you just learned to the following. Lug fep kiki with. What is that? Lug fep kiki with. If you don't remember what lug is blue and with is green. Yeah, 3 dots follows green. And what is with kiki dax blichet lug? Blicket lug. Again, you can go backwards in the slides, but not forwards. Lug is blue, with is green, dax is red, kiki is follows, blicket is around. So green follows red around blue. And you can continue doing that and say you're given these rules. So green follows red around blue, and then there is blue follows green 3 times, and then there is green around red following blue. This is given to the participants, and now you've learned the language, okay? So this was your support set, okay? Now you've learned the language, you've had 3 minutes, you learned this nonce language, and now the test. Here comes the test. Please take 2 minutes and write down the following 5 sentences. Write them down within 2 minutes. Want to gauge our performance. Zub FEP, Zub Kikidax, etc. You can go back, but not forward in the slides. Yep. Humans, given the previous functions as support set without looking back at them, but just giving them sequentially to read them and look at them once, this is human performance on average. We will see 2 different systems that do 100%, okay? And that's the state of the art. We'll also see a system that not only does 100% on this task, but on an open grammar. So this is a closed grammar. And you'd like to do things other than just make-believe languages. Okay. Here is another example where the human performance is this, and the machine is again 100%. So essentially, in the language of meta-learning, the first functions that we got here were our support set, whereas the query set is here. Okay, these are the query set. Okay, so let's begin by describing systems that actually solve this at 100%. Well, meta-learning does better than just a sequence-to-sequence model, and self-supervised meta-learning does better than meta-learning, but self-supervised meta-learning with a meta-grammar actually solves this 100%. And so let's see this in action. Okay, so first, meta-learning. In meta-learning, we have support sets. Support sets can be mappings from inputs to outputs. So for example, run twice and run. Look thrice, look. These are examples in our support set, and we have a neural memory embedding or an embedding here. And then given a query set, look twice, we have a neural translation system that outputs look. So I guess this is exactly the architecture of meta-learning that we drew a month ago, where we have a function, a meta-learning function G that outputs a learning algorithm that's given a query set. And this often fails on long and complex inputs, and we'll see a comparison with meta-learning. So you can form, this example is meta-learning and see this algorithm, and we'll go back to this. So here's the self-supervised meta-learning with a grammar architecture. There are support and query sets. But in this case, the mapping is from our examples to a grammar and a distribution over grammars. So essentially and it's self-supervised. So essentially we have support examples, run twice, run, look twice, look. And then we have a neural model that actually outputs grammars. Grammars are a set of definitions and rules here, informally speaking. And these grammars are essentially synthesized or sampled from the space of possible grammars. Just sample. And then you can check or search each of these grammars whether they are consistent with the support example. You can run the input of the support example. So the support example D1 has this support example here on the left has x1, y1, run twice and run, x2, y2, look twice and look. You can run x1 through the grammar G and see what happens. Well, and is it y1? Well, if you put run twice through the first grammar, you get and put the fact that the output is y1 is run, you get that run maps to capital word run, look to capital word look, x twice in this case for this grammar maps to xxx, and x thrice to xx. This was just randomly sampled. So this was made up. Now we want to check, is this made up grammar correct or not? Well, let's check. If we feed run twice into this first grammar here, the output we get is run. Now we check, is run consistent with run on the left? No, it's not. So we cross this grammar out. And then we can say, hey, look at this second grammar. This grammar G is run to look to run, x twice xx, x thrice xxx. Well, it gets the twice right, but it turns run to look. So we pass run twice, the input here, through the grammar. We get look. It doesn't match, so we disqualify this grammar. And then we look at continue, searching through the grammars until we find a grammar that satisfies both the first and the second examples. And again, each example in the support has input-output pairs as an input and output. And this grammar, the third grammar with the dashed line around it, satisfies all the support examples. Okay, so we take that grammar and we apply it to our query set. And then we get in our query set look twice, and we apply this grammar that worked, that was consistent with the grammars on the support set, and we get look. So let's just define this formally. The support set of input-output examples, capital X, is just xi, yi. The query set of inputs is qi. And the program maps qi to ri, namely the grammar or the program gets the query and maps it to the response ri. We can think of this as a reward as well. Well, the reward is checking if g of xi matches yi for our support set. Now, training given a support set x of input-output examples, it's a small set, predict a program G explaining the support and query sets. And now we need to tackle the representation. Well, specifically, how to represent X, right? We can't just draw circles. There should be a representation here. Well, we have an encoder, and that encoder represents X. In this case, it's a function of the input and a function of the output, concatenated, multiplied by a matrix W, passed through a nonlinearity ReLU, and that's the encoder of our support set. And then there is a decoder of the output of the encoder given a latent hidden variable U0, which is the sum of HI, and this decoder is essentially estimating the probability of the grammar given X. So here is the encoder and the decoder. We have X, our support examples on the left. Okay, so here we have the input and output for each support example. Each one of them is passed through an encoder. And so we see the encoder for DAX-FEP, which is FI, through an LSTM, and then the encoder for red, which is FO, through an LSTM. They're concatenated and multiplied by the matrix W. So are the others. And then these are passed through a decoder, and that decoder's goal is to generate the grammar G. And one of these grammars is shown here in the middle. And then once we have the grammar, we can take this grammar and apply it to a different query set. Okay, for example, on the right here, we have G applied to duplicate with Kiki DAX-FEP. Okay, so if I remember correctly, duplicate yellow around green, following red 3 times. Okay, so we can parse this by the grammar. We follow the grammar. Notice that we take x2 Kiki x1, which is x1 x2, and u2 FEP, which is u2 u2, duplicate with u1 blicate u2, u1 around u2. And so we put in, we follow the rules of the grammar, and we get red, yellow, green, yellow. This is a hard problem. There are many grammars. How do we find the correct one? Do we just randomly sample grammars until we find one that's consistent with the input? It is taking, it is using gradient descent. So the algorithm is a self-supervised generation of the training data. You randomly sample a grammar G. You randomly sample a set of inputs that are consistent with the grammar. You apply the grammar to each input sequence to produce the output. You generate the support set of input-output examples, and then you train the parameters of the network by gradient descent. So essentially, the grammar is our transformation. It's our self-supervised transformation that we are defining by a program here. This is a recipe for uncovering these rules. Okay, and some results comparing just meta-learning in green and meta-learning with a metagrammar in without search in orange, and meta-learning with a metagrammar with search in blue. It's self-supervised. Meta-learning with a metagrammar performs 100%. Here is example of the data. X, walk maps to walk left twice is left turn, walk, jump is jump around left turn, jump, etc., and walk right. This is a data set that's a benchmark in the field. And that data set is X, capital X, and we're mapping a data set of pairs to a grammar, to a program. So remember, we're not doing supervised learning, we're doing meta-learning. Meta-learning takes in inputs that are themselves input-output pairs. That's what we have here. Capital X is our D in meta-learning. And we're learning an algorithm that learns to learn. That's the meta-learning algorithm, the grammar here. G, that when we apply it, learns various query examples. Length, simple, jump, and write are various test cases depending on what's given in the training. And here, synth is the meta-learning using the metagrammar, so with self-supervised learning without search, and synth R's at the top is Nye's, Lakes et al. Self-supervised meta-learning with meta-grammar. This can be used for on math word data. So here is X is the data of Japanese symbols for numbers. And here is the grammar. And you can see the quality of the results on learning math data with different languages where the symbols are unknown. Each sample is a mapping, and we're mapping instead to a label, we're mapping to a grammar or to a function or to a learning algorithm that itself is taking the input and then producing the output. So